everyone's talking about going to Mars, but almost nobody is talking about what it actually takes to stay. Most people think colonizing Mars is an engineering problem. Build the habitat, flip the switch, done. The biggest thing standing between humanity and Mars isn't a rocket, a budget, or even the distance. It's you, your bones, your brain, your biology. If you want to understand the universe at a deeper level, make sure to give this video a like. Now let's get started. Let's start with distance, but not in the way you've probably heard it framed before. You already know Mars is far. That's not the interesting part. The interesting part is what far actually means in the context of keeping a colony alive. Because Mars isn't sitting at a fixed point in space waiting for us. It's moving. Earth is moving. Both planets are orbiting the Sun. Earth at roughly 29.8 kilometers per second. Mars at roughly 24.1 kilometers per second. They're on different tracks, at different speeds, and the gap between them is constantly changing. At their closest approach, called opposition, which happens roughly every 26 months, Mars is about 54.6 million kilometers away. That sounds enormous, and it is. But at their furthest, when the two planets are on opposite sides of the Sun, that distance balloons to around 401 million kilometers. That variability matters enormously for mission planning. Here's why. The most fuel-efficient way to get from Earth to Mars isn't a straight line, because there is no straight line in orbital mechanics. You ride a curved path called a Hohmann transfer orbit, an elliptical arc that stretches between the orbit of Earth and the orbit of Mars, using the Sun's gravity as an anchor. And that path only lines up favorably every 26 months. Miss the window, and you are waiting more than 2 years for the next one. The transit time on that path, between 6 and 9 months one way. 6 to 9 months of your crew sealed inside a pressurized habitat, exposed to deep space radiation, burning muscle and bone. And this is something researchers are now genuinely worried about. Potentially experiencing measurable changes in cognitive function. A study published in 2014 in the journal PLOS One looked at astronauts who had completed long-duration missions and found statistically significant reductions in white matter volume in parts of the brain associated with motor coordination and sensory processing. We are, quite literally, talking about spaceflight altering the structure of the human brain, and that research has only deepened since then. A 2019 NASA-funded study using mice as proxies for human biology found that simulated deep space radiation caused significant neurological damage, anxiety-like behavior, memory deficits, disruptions in how neurons communicate within weeks of exposure. Now picture that playing out over 6 to 9 months of actual travel. Your colonists don't arrive on Mars healthy, rested, and ready to build. They arrive depleted, physically compromised, and in need of serious recovery time on a planet that offers no hospitals, no emergency services, and an atmosphere so thin it would kill you in under 2 minutes if your suit failed. That's the starting point. That's day one. Now let's talk about something that deserves far more public attention than it gets: radiation. Because this is one of those issues where the numbers, when you actually lay them out, are sobering in a way that no amount of optimistic framing can fully soften. Here on Earth, you have two extraordinary shields protecting you at all times. The first is the magnetosphere, a vast invisible cocoon of magnetic energy generated by our planet's liquid outer iron core, which deflects the charged particles of the solar wind and the high-energy cosmic rays that stream in from across the galaxy. The second is the atmosphere, roughly 10,000 kilograms of gas stacked above every square meter of the surface, absorbing and scattering the radiation that does manage to get through. Mars has neither of these. Not anymore. This is one of the great tragedies in planetary science. Around 3.5 to 4 billion years ago, give or take, Mars's internal dynamo died. The planet's core, smaller and cooling faster than Earth's, solidified. The magnetic field it had been generating collapsed, and without that protective shield, the solar wind went to work on Mars's atmosphere, slowly, relentlessly, over hundreds of millions of years, stripping it away particle by particle. Today, Mars's atmosphere is roughly 1% as dense as Earth's. The atmospheric pressure at the Martian surface is about 630 pascals. Compare that to Earth's 101,325 pascals. You couldn't breathe it even if it were pure oxygen. It simply isn't enough to push air into your lungs, and without a meaningful atmosphere or a magnetic field, the surface of Mars is bathed in radiation. The NASA Curiosity rover, which has been crawling across Gale Crater since 2012, carries a radiation detector called the Radiation Assessment Detector, and the numbers it has sent back are striking. The average daily surface dose on Mars is approximately 233 microsieverts. On Earth, the average person receives roughly 8 microsieverts per day from natural background radiation. Airline pilots, some of the most radiation-exposed workers on the planet due to their altitude, receive around 2.2 millisieverts per year. A Mars colonist living on the surface without heavy shielding would accumulate radiation doses equivalent to a full-body CT scan roughly every 5 to 6 days, week after week, month after month, year after year. The cumulative cancer risk over a standard mission duration of 500 days would exceed the lifetime limits currently set by NASA for its astronauts, limits that are themselves already considered generous compared to occupational standards for radiation workers here on Earth. Over the long term, this level of exposure doesn't just raise cancer risk. It damages the DNA repair mechanisms inside cells, suppresses immune function, accelerates the development of cataracts, and based on emerging research, may contribute to early-onset cardiovascular disease and neurodegeneration. This is not a footnote in the colonization plan. This is a central, defining challenge, and the solutions being seriously discussed. Building habitats underground, using Martian regolith as radiation shielding, constructing pressurized lava tube settlements, all add layers of complexity, cost, and time to any realistic colonization timeline. Let's talk about a number that doesn't show up in rocket launch announcements or colonization timelines, but that every serious scientist working on this problem knows about. That number is 160. 160 is, roughly, the minimum number of unrelated individuals that some population geneticists have argued you would need to found a genetically viable colony, one capable of sustaining itself across multiple generations without the slow creep of inbreeding depression. But here's the thing. More recent and more rigorous modeling has pushed that number significantly higher. A 2022 study published in the journal Scientific Reports, led by researcher Cameron Smith from Portland State University, ran detailed population simulations specifically for interstellar colonization. But the underlying biology applies directly to Mars. The conclusion? To maintain genetic diversity, buffer against random genetic drift, and survive catastrophic events like disease outbreaks or accidents, you would need a founding population of somewhere between 10,000 and 40,000 individuals. Not 100, not 1,000, tens of thousands. Sit with that for a moment. Every romantic vision of a small, scrappy crew of pioneers building the first Martian city has to be weighed against this biological reality. A group of 100 people, or even 1,000, isn't a civilization. It's a colony in the fragile, precarious sense of the word. One bad outbreak of a respiratory illness, one catastrophic habitat failure, one failed crop cycle, and you're not just losing lives, you're potentially collapsing the entire genetic foundation of the settlement. This is why researchers who specialize in long-term civilizational planning talk about Mars colonization not as a single mission, but as a sustained, multi-decade pipeline of people and resources flowing continuously between two planets. You aren't launching one crew. You are launching dozens of crews, year after year, mission window after mission window, for potentially half a century or more, before the population even begins to approach the threshold where it could reasonably call itself self-sustaining. And that pipeline has a choke point built right into it, that 26-month gap between optimal launch windows. Even if you sent 400 people per window, which would be an extraordinary, historically unprecedented logistical achievement, it would take you roughly 12 to 13 launch windows, spread across more than 25 years, just to move 80,000 people to Mars. 25 years of flawless execution, with no mission failures, no political disruptions, no funding crises, no pandemics. That's the optimistic version. The realistic version involves all of those things happening, because that is how large human endeavors unfold across time. Always have, always will. Now here's where the conversation shifts from population biology to something even more layered, and honestly, something more beautiful. Because once you start thinking about what it actually means to build a civilization from scratch on another world, you stop thinking purely about logistics and start thinking about something closer to anthropology, to history, to the deep patterns of how humans actually organize themselves when they're starting over. Think about the earliest human settlements on Earth. The first permanent agricultural communities emerging around 12,000 years ago in what is now the Middle East, places like Jericho and Çatalhöyük. Those settlements didn't appear because someone sat down with a master plan and executed it. They emerged slowly, messily, through trial and error, through failed harvests and rediscovered techniques, through conflict and cooperation, and the slow accumulation of locally specific knowledge about how to survive in a particular environment. Mars colonists will face an almost identical process, except compressed, except happening under conditions and so extreme that the margin for error is essentially zero. Every single thing that Earth settlers could eventually fall back on, hunting wild animals when crops failed, drinking from rivers, breathing the outside air, walking into a forest and finding wood for shelter, is completely unavailable on Mars. There is no fallback, there is no outside. The habitat is everything. If the habitat fails, the colony fails, and that is not a recoverable situation. This is why the concept of what researchers call a closed-loop life support system is so central to Mars colonization, and why it is so technically difficult to achieve. A closed-loop system is exactly what it sounds like, a system that recycles everything. Water is captured, filtered, and returned to the supply. Carbon dioxide exhaled by the crew is chemically converted back into oxygen. Organic waste is composted and returned to the soil to grow food. Nothing is wasted, nothing is allowed to exit the loop. The International Space Station runs a partial version of this. The water recovery system on the ISS can recycle roughly 90 to 93% of the water on board. Urine, sweat, moisture from exhaled breath back into drinkable water. That's genuinely impressive. But 90 to 93% is not 100%, and on Mars, even a 2% loss rate, compounded day after day across a large population, represents an enormous drain on resources that cannot be easily replenished. NASA's ongoing work through programs like the Advanced Life Support Project and research conducted at facilities like the Kennedy Space Center's Space Life Sciences Laboratory has been pushing these recycling efficiencies higher. But the gap between what we can currently achieve and what a truly closed, self-sustaining Martian ecosystem would require is still significant. And food is perhaps the most tangible version of this challenge. Growing food on Mars is not impossible, but it is extraordinarily complicated. and the popular image of someone in a spacesuit planting potatoes in Martian soil, inspired, of course, by a certain beloved film, is a dramatic oversimplification of what would actually be involved. Martian regolith, the loose material covering the surface, is not soil in any biological sense. It doesn't contain the organic matter, the microbial communities, the nitrogen-fixing bacteria, or the complex chemical balances that make Earth's soil capable of sustaining plant life. What it does contain, in troubling concentrations, is a class of chemicals called perchlorates. Perchlorates are oxidizing salts that are toxic to most plants at the concentrations found in Martian regolith, around 0.5 to 1% by weight, and that also happen to be a serious health hazard for humans, interfering with thyroid function at even relatively low doses. Every kilogram of Martian soil used for agriculture would need to be processed, leached to remove perchlorates, amended with organic material and the right microbial communities, and carefully monitored for chemical balance before anything edible could be grown in it reliably. The NASA-funded research group studying in situ resource utilization for Mars has been working on exactly this problem with some promising early results, but the scale of the challenge when you're thinking about feeding thousands or tens of thousands of people continuously is breathtaking. The likely solution involves a layered approach. Hydroponics and aeroponics, growing plants in nutrient-rich water or air solutions without any soil at all, would handle the majority of food production in the early colony, offering faster growth cycles, greater water efficiency, and far better control over contamination risks. Treated regolith agriculture might supplement this over time as soil remediation techniques mature, and microbial food production, growing algae, fungi, and lab-cultivated proteins, would provide dense, efficient caloric and nutritional sources that require far less physical space than conventional crops. But all of this infrastructure, the grow lights, the water systems, the processing equipment, the monitoring technology, needs to be built, powered, maintained, and scaled. And that brings us directly to the next layer of the problem: energy. Everything on Mars runs on energy. Heat, because the average surface temperature is around -60 degrees Celsius, swinging from about -125 degrees near the poles in winter to as much as +20 degrees near the equator on a summer afternoon. Oxygen generation, water recycling, food production, communications, transportation across the surface, medical equipment, computing systems, every single one of these requires power, and that power has to come from somewhere. The two most discussed sources are solar and nuclear. Solar energy on Mars is complicated by one crucial factor. Mars is roughly 1.52 times farther from the Sun than Earth is. Because of the inverse square law of light intensity, that means Mars receives about 43% of the solar energy per square meter that Earth receives, already a significant reduction. Then factor in the Martian atmosphere, thin as it is, which does scatter and absorb some sunlight, and the regular global dust storms that can reduce solar panel output by up to 99% for weeks or months at a time. The dust storm of 2018, which lasted roughly 6 to 8 months, and ultimately ended the Opportunity rover's mission after nearly 15 years of operation, is a vivid illustration of what solar-dependent surface infrastructure on Mars would face. A colony powered primarily by solar panels during a storm of that duration isn't just inconvenienced. It's in a survival situation. Nuclear power, and specifically small modular fission reactors, is increasingly seen as the more reliable long-term energy backbone for a Mars colony. NASA and the Department of Energy's Kilopower project, now evolving into the Fission Surface Power Program, has been developing compact fission reactors specifically designed for surface operations on the Moon and Mars. The initial designs aim to produce around 10 kilowatts of power continuously regardless of sunlight or dust conditions. Scaling that up to the megawatt level output, a large colony would need means deploying many of these units, and manufacturing, transporting, and safely operating fission reactors in a remote, resource-constrained environment introduces its own cascade of engineering and safety challenges. All of this, the biology, the genetics, the food systems, the energy infrastructure, feeds into a timeline that looks very different from what you might have absorbed from news headlines. And yet there's a layer underneath all of this that we haven't even touched yet, something that might actually be the strangest and most profound challenge of all. What happens to the human mind when you take it off Earth permanently? Not for 6 months, not for a year, for a lifetime, for generations. What happens to children born on Mars, under 38% of Earth's gravity, who never feel rain, never smell a forest, never look up and see an open blue sky? What happens to their bones, their muscles, their vestibular systems, their psychology? And what does it mean for their identity? Are they Martians? Are they human in the same sense that we are? These questions aren't science fiction anymore. They're the questions that developmental biologists, neuroscientists, and ethicists are starting to grapple with seriously, and the answers, incomplete, preliminary, often uncomfortable, are going to reshape everything you think you know about what colonizing Mars actually means for our species. That's where we're going now, and I promise you, it gets stranger and more extraordinary from here. There is a word that scientists use when they talk about organisms adapting to new environments over generations. That word is selection pressure, and it is one of the most powerful forces in the entire history of life on Earth. Every creature alive today, every plant, every insect, every mammal, every microbe is the product of billions of years of selection pressure. Environments pushing on biology, rewarding certain traits, punishing others, slowly sculpting living things into forms that fit their world more precisely than any human engineer could deliberately design. Now here is the question that keeps some of the most serious biologists and anthropologists up at night. What happens when you take a species shaped entirely by one world, its gravity, its radiation levels, its atmospheric composition, its day length, its seasonal cycles, and plant it permanently on a completely different one, not for a visit, not for a mission, forever? Because here's the thing about Mars that rarely gets discussed in the context of colonization timelines. Mars has 37.6% of Earth's surface gravity. Not zero gravity like the International Space Station, which we know causes serious physiological problems over time, but not Earth gravity either, something in between. Something that has never existed in the entire evolutionary history of our species, and we have essentially no data on what living in that gravitational environment does to the human body over years, let alone over a lifetime, let alone across multiple generations. We know what zero gravity does because astronauts on the ISS have given us a detailed, sobering picture. In microgravity, bones lose density at roughly 1 to 2% per month in the load-bearing regions. Muscles atrophy. The cardiovascular system weakens because it no longer has to work against gravity to pump blood upward. Fluids shift toward the head, causing intracranial pressure increases that can permanently damage vision, a condition called spaceflight-associated neuroocular syndrome, or SANS, which has been found in a significant proportion of astronauts who complete long-duration missions. The spine elongates, the immune system behaves abnormally, all of that from zero gravity, but 37.6%. We genuinely don't know. It might be enough to prevent the worst of these effects. It might not be. It might cause its own completely unique set of problems that we won't fully understand until people have actually lived in it for extended periods, which means the first generation of permanent Mars colonists will, in a very real sense, be living subjects in an unprecedented long-term biological experiment, and their children will be something genuinely new. A child conceived and born on Mars will develop in 37.6% gravity from the very first moment their body begins to form. Their skeleton will grow in response to that gravitational load, not Earth's. Their muscles will calibrate to that environment. Their sense of balance and spatial orientation processed through the vestibular system in the inner ear, a system exquisitely tuned by millions of years of Earth gravity evolution, will form around Martian conditions. If that child were ever to travel to Earth, they might find it physically overwhelming. Earth's gravity could feel crushing to a body that was never shaped to carry it. Researchers speculating about this scenario, and it is still largely speculative because we simply don't have the data, have suggested that second or third generation Martians might be physically incapable of living on Earth without significant medical intervention. Their hearts might not be strong enough to pump blood efficiently in a full gravity field. Their bones might fracture under loads that an Earth-born person handles without a second thought. Within perhaps 3 to 5 generations, a span of roughly 75 to 150 years under current human lifespan projections, though that may itself change significantly with advancing medicine, the Martian population could begin to diverge biologically from the Earth population in ways that are subtle at first and then increasingly pronounced. Not dramatically, not quickly by evolutionary standards, but measurably, detectably, meaningfully. This is not science fiction. This is basic evolutionary biology applied to a new context. And it raises a question that is simultaneously scientific, philosophical, and deeply human. At what point does a Martian-born population stop being Earth humans who happen to live on Mars and start being something else, something new? The answer to that question has enormous implications for the colonization timeline, because it fundamentally changes what the endpoint looks like. If the goal is a self-sustaining Mars colony that maintains a continuous biological and cultural connection to Earth, that's one kind of project. But if, as the biology suggests, the populations will inevitably diverge over generations, then what you are actually building is not just a colony. You are initiating a speciation event, the first planned, conscious speciation event in the history of intelligence on this planet. That is an almost incomprehensible thing to sit with, and yet it follows directly and logically from the science. Now let's talk about the mind, because the body is only half of the picture. The psychological dimension of long-term Mars colonization is one of the most actively studied and least publicly discussed aspects of the entire project. And the findings coming out of isolation and confinement research over the last 2 decades paint a picture that is, to put it plainly, deeply challenging. Human beings are not psychologically built for permanent, sealed isolation from the natural world. We evolved in open environments, under open skies, with access to natural light that shifts throughout the day, triggering hormonal rhythms that regulate sleep, mood, appetite, and immune function, with access to green spaces, running water, the sounds of wind and rain and living things, with social structures that include large, diverse communities rather than small, tightly enclosed groups living in enforced proximity under extreme stress. The research institution that has studied this most rigorously is probably the Russian Academy of Sciences, through the Mars 500 experiment conducted between 2010 and 2011. 6 volunteers, 4 Russian, 1 French, 1 Chinese, spent 520 days sealed inside a series of interconnected modules in Moscow, simulating a full Mars mission including a surface landing phase, no windows to the outside, no fresh air, carefully controlled food supplies, a communication delay with the outside world that simulated the actual signal lag between Earth and Mars, which can range from 3 to 22 minutes one way, depending on orbital positions. The results were illuminating and, in places, uncomfortable. By the end of the experiment, several crew members showed significant disruptions in their circadian rhythms. Their internal body clocks had drifted and fragmented, leading to irregular sleep patterns that persisted even after the experiment concluded. 2 crew members developed what researchers described as severe psychological sedentariness, a kind of behavioral shutdown where motivation to do anything beyond the bare minimum collapsed almost entirely. Physical activity dropped dramatically. Social interaction within the crew became increasingly strained, and this was 520 days with the knowledge that the outside world was right there, that they could end the experiment if they chose to, that their families were accessible by phone, that Earth's natural environments were a short walk away once the doors opened. On Mars, there are no doors you can simply open. There is no outside world waiting for you. The psychological weight of true permanent isolation from everything your species evolved alongside, the open sky, the wind, the rain, the smell of soil after rainfall, the sound of birds, is something we have never actually tested on any human being, because we have never actually put any human being in that situation. Some researchers argue that this psychological challenge is so fundamental that solving it needs to be treated as seriously as solving the radiation problem or the food production problem. That designing for mental well-being through habitat design that incorporates natural light simulation, large communal green spaces, carefully managed social structures, access to art and music and meaningful creative work isn't a luxury in a Mars colony, it's infrastructure. As critical as the water recycling system or the power grid, and then there is the communication problem, which sounds mundane until you really think through its implications. The speed of light is roughly 299,792 kilometers per second. That sounds fast, and by human standards it is almost incomprehensibly fast. But space is so vast that even at that speed, a signal from Earth to Mars takes between 3 and 22 minutes to arrive, depending on orbital geometry. The round-trip communication delay, send a message, wait for a response, is therefore between 6 and 44 minutes. Think about what that means in practice. If a medical emergency occurs in the Mars habitat, the colony's medical team cannot call a specialist on Earth and get real-time guidance. By the time their message arrives and a response is sent back, nearly an hour might have passed. If a critical system fails, ground control on Earth cannot troubleshoot it in real time. If a political crisis emerges, a dispute over resources, leadership, the direction of the colony, there is no immediate recourse to Earth's governing structures. The Mars colony will be, of necessity, functionally autonomous, self-governing, making life and death decisions without the ability to consult with the larger civilization that sent it there. And that autonomy has to be baked into the colony's social and political architecture from the very beginning, because the alternative, a community of thousands of people waiting up to 44 minutes for answers to urgent questions, is not a viable way to run a civilization. What kind of governance structure works for a community like that? What legal frameworks apply? Who has authority? How are disputes resolved? These questions are not peripheral to the colonization timeline. They are central to it, because history is full of examples of colonies that had the physical infrastructure to survive but collapsed anyway, through internal conflict, through power struggles, through the failure to develop governance systems capable of managing the stresses of an extreme environment. The successful colonization of Mars will require not just engineers and scientists and biologists. It will require political theorists, sociologists, psychologists, anthropologists, ethicists, and historians who understand deeply how human communities organize themselves under pressure and who can help design social systems robust enough to hold together across decades and generations. Here's what ties all of this together in a way that I find genuinely extraordinary. We are not the first generation to face the challenge of building something from nothing in a hostile and unfamiliar environment. Every great human migration in history, across land bridges, across open oceans, into deserts and mountain ranges and Arctic tundra, involve people stepping beyond the edge of the known world with inadequate tools, incomplete knowledge, and no guarantee of success. The difference is that those migrations were driven by gradual necessity, by the slow push of climate change and population pressure, and the pull of undiscovered resources. The colonization of Mars, if it happens, will be different in one extraordinary way. It will be chosen, deliberate. A species consciously deciding to extend itself beyond its home world, not because it has to, but because it can, because it's curious, because something deep in the structure of human consciousness looks at the horizon and wants to know what's on the other side. Carl Sagan wrote in 1994, in his book Pale Blue Dot, that the surface of the Earth is the shore of the cosmic ocean. On this shore, we have learned most of what we know. Recently, we have waded a little out to sea, enough to dampen our toes, or at most, wet our ankles. Mars is the next wading point, the next depth mark, the next step into the ocean. But what we've been mapping in this video so far is just the surface of the challenge, because we haven't yet talked about the technology that doesn't exist yet, and how long building it will realistically take. We haven't talked about the economics, what colonizing Mars actually costs, and who pays for it. And we haven't talked about the single most important variable in the entire timeline, political will, human decision-making, the messy, unpredictable, deeply human question of whether civilizations actually follow through on their grandest ambitions, or whether they reach the edge of the extraordinary and pull back. Let's talk about the Apollo program for a moment, not because it's a tired reference, but because when you look at it through the right lens, it tells you something deeply important about what it actually takes for a civilization to do something that has never been done before. In 1961, John F. Kennedy stood before the United States Congress and committed his nation to landing a human being on the moon before the end of the decade. At that moment, the United States had accumulated a grand total of 15 minutes and 22 seconds of human spaceflight experience. Alan Shepard's suborbital hop in May of that year, that was it. 15 minutes and 22 seconds, and Kennedy said, "So we are going to the moon." 8 years later, they did it. Now, here is the part that people forget. The Apollo program at its peak consumed roughly 4% of the entire United States federal budget. 4%. In today's terms, that would be somewhere in the range of $100 billion per year. The total cost of the Apollo program across its lifetime has been estimated at around $280 billion in today's currency. It employed at its height around 400,000 people, engineers, scientists, technicians, administrators, contractors, spread across every corner of the country. It was, by almost any measure, the largest peacetime technological mobilization in human history, and it lasted 12 years before the funding was cut, before political will evaporated, before the public, having watched humans walk on the moon 6 times, decided they had seen enough and moved on to other concerns. That trajectory, extraordinary ambition, massive mobilization, stunning achievement, followed by retreat, is not unique to Apollo. It is, in fact, one of the most consistent patterns in the history of large-scale human exploration. The Portuguese and Spanish maritime empires of the 15th and 16th centuries. The great polar expeditions of the early 20th century, the nuclear energy programs of the 1950s and 60s, which promised electricity too cheap to meter and then stalled under the weight of cost overruns, public fear, and political complexity. Great civilizations are capable of extraordinary things, but they are not capable of sustaining extraordinary effort indefinitely, and any honest assessment of the Mars colonization timeline has to grapple with that reality. Right now, in 2026, 3 major entities are publicly committed to sending humans to Mars within the next decade or so. NASA, with its Artemis program serving as a stepping stone through lunar operations. The European Space Agency, through various collaborative frameworks, and SpaceX, Elon Musk's private aerospace company, which has perhaps the most aggressive and specific public timeline of any organization on Earth. Musk has, at various points, stated his intention to send uncrewed Starship vehicles to Mars as early as 2026, with crewed missions potentially following in 2028 or 2029. He has spoken publicly about wanting to establish a self-sustaining city on Mars within 20 years, with a population of 1 million people within 50 years. Let's hold those numbers up against everything we've discussed so far and ask honestly, what does the science say? The 2026 uncrewed mission window is technically plausible because 2026 is indeed a favorable Mars launch window, and SpaceX's Starship, the largest and most powerful rocket ever built, with its first successful orbital flight achieved in 2024, is at least theoretically capable of the transit. Uncrewed cargo missions to Mars are the necessary first step, establishing surface infrastructure, testing landing systems, pre-positioning supplies before any human ever attempts the journey. But crewed missions in 2028? That timeline would require not just successful uncrewed landings, but the development and validation of life support systems for the surface, radiation shielding solutions, reliable power generation, and the medical protocols for managing a crew through a 6 to 9 month transit and an extended surface stay, all within roughly 2 years of the first crewed mission's launch date. The engineering community's consensus, while respectful of SpaceX's remarkable track record of compressing development timelines, is that this is extremely ambitious. The phrase that comes up most often in peer-reviewed discussions is technically achievable but operationally unprecedented. NASA's own internal roadmap, as of the most recent publicly available planning documents, targets human Mars missions in the late 2030s at the earliest, roughly a decade behind SpaceX's stated ambitions. And NASA's timeline includes the assumption of sustained congressional funding, successful completion of the Artemis lunar program as a proving ground for deep space operations, and the development of nuclear thermal propulsion systems that could reduce transit times and therefore radiation exposure for crews. Nuclear thermal propulsion, engines that use a nuclear reactor to superheat a propellant like liquid hydrogen, generating far more thrust efficiency than chemical rockets, has been in development in various forms since the 1960s. The NERVA program, tested extensively in the 1960s and early 1970s, demonstrated that nuclear thermal engines could achieve roughly twice the efficiency of the best chemical rockets available. The program was cancelled in 1972, not because it didn't work, but because the moon missions were over and Mars wasn't on the immediate agenda. NASA and DARPA have been jointly funding a revival of this technology through the demonstration rocket for Agile Cislunar Operations program, known as DRACO, with an in-space demonstration targeted for the mid-2020s. If nuclear thermal propulsion matures as hoped, transit times to Mars could be reduced from 6 to 9 months to perhaps 4 to 5 months, a meaningful reduction in radiation exposure and physiological stress for crews. But if is doing a lot of work in that sentence, and the development timeline for new propulsion technologies has historically been measured in decades, not years. The economics of Mars colonization are, if anything, even more sobering than the technology gaps. NASA has never publicly released a comprehensive cost estimate for a full human Mars mission, partly because the mission architecture keeps evolving, and partly because the number, when modeled rigorously, is politically uncomfortable. Independent analyses have suggested that a single crewed Mars landing mission, not a colony, just a landing and return, could cost somewhere between $100 billion and $500 billion, depending on the architecture chosen, the development costs of new systems, and the number of missions required to validate the approach. For context, the entire annual budget of NASA in 2024 was roughly $25 billion. The International Space Station, over its full lifetime from initial construction through projected retirement, is estimated to have cost around $150 billion in total. Mars colonization is not a single mission cost. It is a generational financial commitment that dwarfs anything humanity has previously attempted. SpaceX's approach attempts to change this equation fundamentally through the principle of full reusability. If Starship can be built, launched, refueled in orbit, sent to Mars, and then critically returned to Earth and launched again, the cost per kilogram delivered to Mars drops by orders of magnitude compared to expendable rocket architectures. Musk has spoken about targeting a cost of around $100,000 per ton delivered to Mars at scale, dramatically lower than current estimates for expendable systems. Whether those numbers are achievable at the scale required for genuine colonization is a question that serious aerospace economists debate actively. The optimists point to SpaceX's genuine track record of cost reduction in launch services. The Falcon 9 did fundamentally change the economics of getting to low Earth orbit. The skeptics point out that full reusability across interplanetary distances introduces engineering challenges that have no precedent, and that Musk's public cost estimates have historically been optimistic by significant margins. The truth, as it so often does, probably lives somewhere between those poles. The cost of reaching Mars will almost certainly come down substantially from current estimates as technology matures and launch cadences increase. Whether it comes down enough, fast enough, to make the kind of sustained multi-decade population pipeline that the geneticists say is necessary into an economically viable project, that remains genuinely uncertain. But here is what strikes me as the most interesting and most underappreciated dimension of the economic challenge. It isn't just about how much it costs to get there. It's about how you build an economy once you arrive. A colony that depends entirely on resupply from Earth is not, in any meaningful sense, a self-sustaining civilization. It's a very expensive outpost. The moment a supply ship fails to arrive, whether because of a mission failure, a funding crisis, a political decision on Earth, or simply the brutal arithmetic of the 26-month launch window, a colony that hasn't developed the ability to produce what it needs locally is in immediate danger. This is why the concept of in-situ resource utilization, using the resources available on Mars itself to produce what the colony needs, is so central to every serious colonization plan. And the resources available on Mars, while not abundant in the way Earth's are genuinely interesting. The Martian atmosphere, thin as it is approximately 95.3% carbon dioxide. That carbon dioxide can be split through a process called electrolysis combined with the Sabatier reaction to produce oxygen and methane, the exact combination of propellants that SpaceX's Raptor engines use. This means that, in principle, a Mars colony could produce its own rocket fuel from the local atmosphere, enabling the return journey without having to carry all the propellant from Earth. NASA actually demonstrated this on a small scale with the MOXIE experiment aboard the Perseverance rover, which successfully produced oxygen from Martian atmospheric carbon dioxide in April 2021. It was a tiny amount, about 10 grams over an hour, roughly the rate at which a small plant produces oxygen, but the proof of concept was real. Mars also has water, not liquid on the surface, because the atmospheric pressure is too low and the temperatures too extreme for liquid water to be stable there. But ice, significant, confirmed deposits of water ice at the poles, and what planetary scientists now believe are substantial subsurface ice deposits at lower latitudes, including the extraordinary discovery announced in January 2024 of a potential ice sheet near the Martian equator, buried under several kilometers of dust and rock, that if confirmed at the scale initially suggested, could contain enough water to cover the entire planet in a shallow ocean, roughly 1.5 meters deep. That discovery, made using data from the European Space Agency's Mars Express orbiter and its MARSIS radar instrument, is genuinely one of the most significant findings in recent Mars science. Because water is not just drinking water. Water is hydrogen and oxygen, oxygen for breathing, hydrogen for fuel, water for agriculture, water for radiation shielding. Water is actually one of the most effective materials for blocking certain types of cosmic radiation. The presence of substantial water ice accessible to a surface colony changes the resource calculus significantly. And yet, even with local resources available, even with in-situ production of fuel and oxygen and water, the colony remains dependent on Earth for one thing that cannot be manufactured on Mars for a very long time: knowledge, expertise, the accumulated technological and scientific understanding that allows complex systems to be built, maintained, and repaired. Every piece of sophisticated equipment in the colony, the life support systems, the medical devices, the computing infrastructure, the power generation systems, the agricultural technology, was designed and built by specialists who spent years or decades developing their expertise. When something breaks in ways that the colony's own engineers and technicians can't diagnose or fix, what happens? When a medical situation arises that exceeds the colony's medical officers' training and equipment, what happens? When a software system fails in ways that require specialized knowledge that nobody on Mars possesses, what happens? The answer, in each case, is that you either solve it with what you have or people die. And that reality shapes the entire approach to colony design in ways that add complexity, cost and time to every part of the timeline. It means the colony needs not just generalist problem solvers, but deep specialists in a remarkable breadth of fields, all simultaneously present in the same small community. It means redundant systems built into every critical function, because when the only atmospheric processor fails and there's no spare part and the next supply ship is 18 months away, redundancy isn't a luxury. It's the difference between survival and catastrophe. And it means the educational systems within the colony, how knowledge is passed to the next generation of Martian-born residents, become one of the most strategically important institutions in the entire settlement. Because a colony that fails to reproduce its own expertise across generations doesn't just stagnate, it slowly loses the ability to maintain the systems its survival depends on. It regresses. And regression on Mars is not an abstract concern. It is an existential one. All of this, the population genetics, the biology, the psychology, the technology gaps, the economics, the governance challenges, the knowledge reproduction problem, feeds into a picture that is simultaneously more difficult and more magnificent than the headlines suggest. Because what we are really talking about when we talk about colonizing Mars is something that has never happened before in the 4.6 billion year history of this solar system. The deliberate, conscious transplantation of a living civilization from one world to another, not a migration forced by necessity, not an accident of geology or climate, a choice made by a species that looked up at the sky, felt the pull of curiosity that has defined it since the first humans sat beside a fire and wondered what lay beyond the horizon and decided to go. The timeline for that, when you take all the science seriously, is long, longer than most people are comfortable hearing. But now is where we start to put real numbers on it, drawing on the actual projections from planetary scientists, mission architects, and the researchers who spend their careers modeling what this would really look like, decade by decade. And I'll tell you this right now, the number that keeps coming up, in paper after paper, from researcher after researcher, is not the one that makes for a good tweet, but it's the honest one. And honest is what we're here for. If you are enjoying this video, make sure to subscribe and give this video a like. It makes a bigger difference than you think, and you won't miss anything. Every video is built around actual research and real missions. Let's put some actual numbers on the table. Because we've spent 4 parts building the foundation, the biology, the psychology, the technology, the economics, the governance, and now it's time to do what the title of this video promises, to actually answer the question, how long would it really take? And to do that properly, we need to separate the question into its component parts. Because colonizing Mars means different things depending on who you ask and what threshold you're using. There's a significant difference between the first human boots on Martian soil, the first permanent crewed outpost, the first settlement capable of surviving a temporary cut-off from Earth, and a fully self-sustaining civilization that could persist indefinitely without any support from its home planet. Each of those milestones has a different timeline, and understanding how they stack is essential to getting an honest answer. So let's build the timeline layer by layer, starting with what's closest, and working outward toward the genuinely long-term horizon, the first humans on Mars. This is the milestone that gets the most attention, generates the most headlines, and has the most publicly stated timelines attached to it. And based on everything currently known, the state of launch vehicle development, the funding commitments of both public space agencies and private companies, the engineering challenges that remain unsolved. The realistic window for the first human Mars landing sits somewhere between the early 2030s and the early 2040s. The optimistic end of that range, say 2028 to 2030, requires SpaceX's Starship to perform flawlessly across a series of increasingly ambitious missions, including uncrewed Mars landings in 2026 that successfully demonstrate surface operations, life support, and propellant production. It requires sustained funding and political commitment from whatever governments are involved, and it requires no major mission failures, no lost vehicles, no crew emergencies, no catastrophic system malfunctions across a development and operational timeline compressed to a degree that has no precedent in the history of human spaceflight. The more cautious end of the range, late 2030s, reflects the historical development timelines for new crewed spacecraft systems, which have consistently taken longer and cost more than initial projections suggested. The Space Shuttle, originally projected to cost around $5.5 million per flight, ultimately cost around $1.5 billion per flight over its operational lifetime. The James Webb Space Telescope, originally scheduled for launch in 2007, finally reached orbit in December 2021, 14 years behind its initial schedule. The Orion spacecraft, which NASA is using as its crewed vehicle for the Artemis program, has been in development since 2004. None of this is a criticism of the people involved in these programs. It is simply an acknowledgement that developing genuinely new technology for the most hostile environment humans have ever attempted to operate in is hard in ways that are consistently underestimated at the outset. The history of spaceflight is, among other things, a long lesson in the gap between projected and actual timelines. So, first humans on Mars, somewhere between 2028 and 2038. Call it the 20s to 30s window. That's the honest bracket, the first permanent crewed outpost. This is meaningfully different from a landing mission. A landing mission is a visit. A crew arrives, conducts surface operations for somewhere between 30 and 500 days, depending on the mission architecture, and then returns to Earth. A permanent outpost means people are there continuously, with crew rotations happening during each launch window, and with the infrastructure being built up progressively with each arriving mission. Getting from first landing to first permanent outpost requires solving a specific set of problems that go beyond what a landing mission demands. You need habitats capable of housing a continuous population rather than a temporary expedition crew. You need food production systems that can supplement resupply missions rather than being entirely dependent on them. You need medical facilities sophisticated enough to handle not just expedition-level emergencies, but the ongoing health needs of a permanent community. And you need power systems robust enough to operate continuously through Martian dust storms and seasonal variations, year after year. The timeline from first landing to first permanent outpost, based on the models developed by mission architects at NASA's Human Research Program and independent researchers like those at the Center for the Utilization of Biological Engineering in Space. A NASA-funded research center based at the University of California is estimated at roughly 10 to 20 years beyond the first landing. If humans first set foot on Mars in the early 2030s, a permanent outpost operating on a continuous basis might be realistic by the mid to late 2040s. If the first landing slips to the late 2030s, you're looking at the 2050s or even the early 2060s before continuous occupation becomes a reality. And that permanent outpost, in its early phase, would be nothing like the image that word might conjure. It would be small, intensely resource-constrained, dependent on Earth for the majority of its consumables, populated by perhaps a few dozen to a few hundred people at most, nowhere near the genetic viability threshold we discussed a bit ago. It would be an extraordinary human achievement and simultaneously a deeply fragile one, the first Mars settlement capable of surviving temporary isolation from Earth. This is the threshold that planetary scientists and mission architects call early self-sufficiency, the point at which the colony could, if necessary, continue to function through a missed supply window without immediate catastrophic consequences, not full independence, not the ability to thrive without Earth forever, but the ability to survive a gap. This threshold requires food production systems capable of generating a meaningful fraction of the colony's caloric needs locally. It requires manufacturing capabilities that can produce at least the most critical spare parts and consumables in situ. It requires medical capabilities that can handle a wider range of emergencies without Earth's support. And it requires a population large enough that the loss of several individuals to accident, illness, or any of the myriad risks of the Martian environment doesn't threaten the colony's operational continuity. The consensus estimate among researchers who model this milestone specifically, including the work published by Stephen Petranek in his book How We'll Live on Mars, informed by conversations with mission architects at NASA and SpaceX, and the modeling done by researchers like Robert Zubrin of the Mars Society, puts this threshold at somewhere between 20 and 40 years after the establishment of a permanent outpost, which, if you chain the timelines together, means early self-sufficiency on Mars is realistically a late 21st century achievement. Somewhere between 2070 and 2090, under moderately optimistic assumptions, under pessimistic assumptions, accounting for mission failures, funding gaps, political disruptions, and the realistic probability that some of the technological solutions we're counting on take longer to develop than current projections suggest. Early self-sufficiency might not be achieved until the early 22nd century, the 2100s, a timeline that feels abstract and distant from where we're standing right now, but that follows directly and logically from the scale of the challenges involved. And then there is the final milestone, the one that the most serious researchers, the ones who aren't selling anything, the ones who aren't trying to raise investment capital or generate media coverage, keep coming back to when they're asked the honest version of this question: full self-sufficiency, a Martian civilization that could survive the permanent loss of contact with Earth, not just a missed supply window, not a funding gap, the actual permanent end of the relationship between the colony and its home world. A community that has developed the full technological, agricultural, medical, educational, social, and governmental infrastructure to perpetuate itself indefinitely on its own across generations. The numbers attached to this milestone are sobering, not because they represent failure, but because they represent the true scale of what colonizing a planet actually means. Researcher and science writer Kim Stanley Robinson, whose Mars trilogy, published between 1992 and 1996, remains one of the most scientifically grounded explorations of Martian colonization in any medium, has estimated, based on his research into planetary engineering and population dynamics, that full Martian self-sufficiency is a project measured in centuries rather than decades. His fictional timeline spans roughly 200 years, and he has described that as optimistic. Stephen Hawking, before his death in 2018, spoke publicly about the need for humanity to become a multi-planetary species within the next 100 years or face existential risk, but was careful to note that this meant establishing a meaningful presence, not a fully independent civilization within that window. The researchers at the Future of Humanity Institute at Oxford University, before its closure in 2024, produced modeling suggesting that a genuinely self-sustaining Mars colony, one robust enough to survive independently, would require a minimum population in the range of tens of thousands to hundreds of thousands, sophisticated local manufacturing of essentially all critical technologies, and a generational timeline of at minimum 100 years beyond the establishment of the first permanent outpost. Put all of that together: first landing, 2030s to 2040s, first permanent outpost, 2040s to 2060s, early self-sufficiency, 2070s to 2100s, full generational self-sufficiency, 2100s to 2200s. The honest answer to how long it takes to truly colonize Mars is somewhere between 100 and 200 years from now, minimum, and that's under reasonably optimistic conditions. Now, here's where I want to pause and reframe this, because I think the instinctive reaction to those timelines is to feel deflated, to feel like the scale of the challenge makes the endeavor seem futile, or at least impossibly remote from anything that matters to people alive today. But consider this: the people who planted the first agricultural settlements 12,000 years ago in the Fertile Crescent had no idea that what they were doing would eventually produce cities, writing systems, mathematics, philosophy, space programs. They were just trying to eat more reliably next winter. They could not have imagined the civilization their small, fragile, deeply uncertain first steps would eventually make possible. The researchers working on Mars life support systems today, the engineers iterating on Starship's heat shield, the planetary scientists analyzing MOXIE's oxygen production data, the biologists studying plant growth under simulated Martian conditions, the psychologists studying isolation and confinement. None of them will live to see a self-sustaining Mars civilization. And yet every piece of work they do is a brick in its foundation. There is something profoundly moving about that when you let yourself feel it fully. The fact that the timescales involved exceed any individual human lifetime doesn't diminish the significance of the work. If anything, it magnifies it. It places it in the same category as the great cathedrals of medieval Europe, structures that took generations to build, whose architects died long before the final stone was placed. But who built anyway? Because the thing being built mattered more than any individual's ability to see its completion. Carl Sagan understood this. In his 1994 reflections on the Voyager photographs, he wrote about humanity's obligation to survive, not just for our own sake, but as the custodians of life's meaning in this universe. Whether you find that framing religious, secular, philosophical, or simply poetic, the underlying point is the same. The project of extending life and consciousness beyond this single fragile world is not just a technical achievement. It is a moral one, a statement about what kind of species we choose to be. But there is one more dimension to this timeline that we haven't fully explored yet. One that changes the shape of everything we've discussed so far. And it isn't about Mars at all, really. It's about Earth. Because the timeline for colonizing Mars doesn't exist in isolation from what's happening on the planet we're launching from. And the conditions on Earth, political, economic, environmental, social, will shape the Mars colonization timeline as profoundly as any engineering challenge on the Martian surface. Think about what the next 100 years on Earth look like under even moderately realistic projections. Climate change is already reshaping agricultural zones, coastal geography, and the distribution of extreme weather events. The global population is projected to peak somewhere between 9 and 11 billion people by late this century, before potentially beginning to decline. Geopolitical tensions between major spacefaring nations, the United States, China, Russia, and increasingly India and the European Union, will influence not just who goes to Mars and when, but whether international cooperation on the scale that a serious colonization effort requires is even politically possible. The history of large-scale international scientific cooperation is actually more encouraging than the daily news cycle might suggest. The International Space Station, for all its flaws and cost overruns, has maintained continuous human presence in orbit since November 2, 2000, 25 years of uninterrupted human spaceflight at the time of this video, through wars, political crises, diplomatic ruptures, and a global pandemic. The collaborative framework that made that possible is fragile, imperfect, and frequently stressed, but it has held. Whether something analogous can be constructed for Mars, particularly given that China has explicitly stated its own ambition to land humans on Mars by 2050, is one of the most consequential geopolitical questions of the coming decades. A cooperative approach to Mars, with shared infrastructure and shared scientific data, would dramatically accelerate the timeline and reduce the cost for everyone involved. A competitive approach, 2 or more nations racing to plant flags and claim territory, might actually accelerate the first landing milestone, driven by the same political urgency that drove Apollo, but would likely produce a less stable and less scientifically productive long-term outcome. The Outer Space Treaty of 1967, which forms the foundational legal framework for human activity in space, explicitly prohibits national appropriation of celestial bodies. No nation can own the Moon, Mars, or any other world. But the treaty is silent on many questions that a permanent Mars settlement would raise: resource extraction rights, governance jurisdiction, the legal status of children born on Mars, the application of Earth-based legal systems to extraterrestrial communities, The legal architecture for Mars colonization is in 2026 almost entirely unbuilt, and building it, through international negotiation, treaty-making, and the slow, grinding work of multilateral diplomacy, will itself take decades. All of which brings us to a question that I find more fascinating than almost anything else in this entire conversation. And it is a question that no amount of engineering genius or political willpower can fully answer in advance. When the first generation of humans born on Mars grows up, when they reach adulthood in a world they have never chosen to leave, that they know only through screens and stories and the memories of parents who came from somewhere else, what will they want? What will matter to them? What will they build? What will they value? Will they see themselves as an extension of Earth civilization, maintaining cultural and political ties to the world their parents came from? Or will they begin to develop a distinctly Martian identity, shaped by the harsh beauty of their world, by the extraordinary intimacy of living in sealed habitats, by the constant awareness of their own fragility and the ferocious competence required just to survive? Will they feel the pull of Earth the way that descendants of emigrants often feel the pull of an ancestral homeland, a distant, half-mythologized place of origin that shapes their identity without defining it? Or will Earth feel as remote and abstract to them as ancient Mesopotamia feels to us, historically important, intellectually interesting, but fundamentally not their story? These questions have no answers yet. They cannot, because the people who will answer them haven't been born, but they will be. And when they are, when the first human child opens their eyes in a hospital on Mars, draws their first breath of recycled Martian air, and begins the process of growing up on a world their ancestors never touched, something will have changed in the universe that cannot be unchanged. There is a photograph that changed the way humanity understood itself. You might have seen it. It was taken on February 14, 1990, by the Voyager 1 spacecraft at the request of Carl Sagan from a distance of roughly 6 billion kilometers from Earth. In the image, our planet appears as a tiny, pale blue dot, less than a pixel across, suspended in a beam of scattered sunlight against the absolute blackness of deep space. Sagan wrote about that image in words that have since become some of the most quoted in the history of science communication. "Look again at that dot," he wrote. "That's here. That's home. That's us. Every human being who ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher and student, every corrupt politician and every saint, all of them lived and died on that dot. I bring this up not for nostalgia, and not because it's a comfortable thought. I bring it up because it is the essential context for everything we're about to discuss. Because the colonization of Mars is, at its deepest level, the story of that dot deciding to become two dots, of life, conscious, curious, self-aware life, deciding that one world is not enough, and that decision, when you trace its roots back far enough, turns out to have begun not in a rocket factory or a government space agency, but in the structure of life itself. Here is something that biology tells us, quietly and consistently, across every ecosystem on Earth. Life expands, not occasionally, not under special circumstances, always, relentlessly, into every available niche, across every available surface, through every crack and fissure and seemingly uninhabitable extreme environment it can find. Microbes thrive in the superheated vents at the bottom of the ocean, in the ice sheets of Antarctica, in the intensely acidic hot springs of Yellowstone, in the stratosphere itself. Wherever there is energy to be harvested and chemistry that permits even the most rudimentary form of self-replication, life finds a way. This is not a metaphor borrowed from a popular film franchise. It is one of the most robust and consistently observed patterns in the entire 4 billion-year history of terrestrial life. and it raises a question that planetary scientists, astrobiologists, and philosophers of science have been wrestling with for decades. If life on Earth is so relentlessly expansionist, if it fills every niche available to it, then is the colonization of other worlds not just a human ambition, but an expression of something deeper, something encoded into the very nature of life itself? The astrobiologist David Grinspoon, in his 2016 book Earth in Human Hands, argues that we may be approaching a transition point in the history of life on this planet. A moment where a species becomes capable of deliberately extending life beyond its world of origin, moving from what he calls a teenage phase of civilization into something more mature and more intentional, from a civilization that uses its planet unconsciously, extracting and consuming without full awareness of consequences, to one that begins to consciously manage its relationship with its home world and deliberately seeds life into the cosmos beyond it. Whether you find that framing inspiring or presumptuous probably depends on your broader philosophical outlook. But the scientific basis for the observation is solid. We are, by any objective measure, the first species in the known history of life on Earth that has both the capability and the expressed intention to move life to another world. And that is genuinely extraordinary, regardless of how you feel about the timeline or the challenges involved. Now here's where the timeline question gets reframed in a way that I think is both more honest and more interesting than the simple how many years framing. When historians look back at the colonization of Mars, and they will, whether that history is written on Earth or on Mars, or on both simultaneously, they will almost certainly divide it into phases. Not based on calendar years, but based on qualitative transitions in the nature of the human presence there. And understanding those phases gives you a much richer picture of what the timeline actually means than any single number can. Phase 1 is what researchers call the exploration phase. Small crews, short stays or rotating occupations. The primary purpose is scientific, understanding the geology, the climate history, the potential for past or present microbial life, the resources available for future use. The infrastructure built during this phase is minimal and purpose-specific. The human footprint is tiny. The dependency on Earth is essentially total. This phase might last anywhere from 10 to 30 years after the first human landing. Phase 2 is the outpost phase, a permanent, continuously occupied facility, growing infrastructure, the beginning of in-situ resource utilization at meaningful scale, producing oxygen, water, and eventually fuel locally, a small but stable population, measured in dozens to low hundreds. Scientific work continues, but engineering and construction become equally important activities. Dependency on Earth remains high, but begins to decrease incrementally. This phase might span another 20 to 40 years. Phase 3 is the settlement phase, the point at which the human presence on Mars transitions from an outpost, a place people are stationed, to a settlement, a place people choose to live. Children are born, communities develop, cultural institutions emerge, art, music, local traditions, shared stories and references that are distinctly Martian rather than transplanted from Earth. Food production covers a significant fraction of nutritional needs locally. Manufacturing covers a growing fraction of material needs. The population reaches the low thousands. Dependency on Earth continues to decrease, though full self-sufficiency remains a future goal. This phase might span another 30 to 50 years beyond the outpost phase. Phase 4 is the self-sufficiency phase. The colony can survive, not just persist, but genuinely function and grow without support from Earth. It has developed the full technological stack required to maintain and reproduce its critical systems across generations. Its population has reached the genetic viability threshold. Its educational institutions successfully transmit the knowledge base required for civilizational continuity. Its governance systems have matured through the inevitable crises and adaptations that all new political communities go through, and its biological relationship with Earth humans has begun to diverge in measurable, meaningful ways. This phase begins under optimistic assumptions somewhere in the late 21st to mid-22nd century. Phase 5, and this is the one that almost nobody talks about in public discussions of Mars colonization, because it exists so far beyond the horizon of individual human lifespans, is what we might call the divergence phase, the point at which the Martian civilization is no longer simply a colony of Earth, either politically, culturally, or biologically, but a genuinely distinct branch of the human family, a second cradle. A place with its own history, its own identity, its own relationship with the cosmos, looking back at the pale blue dot the way we look back at the African savanna, where our species first stood upright and looked at the stars. That phase begins if the biology and the history and the sociology all play out as the relevant researchers project, somewhere between 100 and 300 years after the establishment of the first permanent outpost, which puts it, depending on when that outpost is established, somewhere between the 22nd and 24th century. These timelines are not guesses. They are not arbitrary numbers pulled from optimistic imagination. They are the product of serious, peer-reviewed research across multiple disciplines: population genetics, biomedical engineering, planetary science, political science, sociology, and economics, applied carefully to the specific conditions that Mars presents. And what strikes me every time I look at them carefully is how consistent they are across researchers who approach the problem from completely different directions, using completely different methodologies, coming from completely different scientific traditions. Whether you ask a population geneticist running demographic models or a biomedical engineer assessing life support requirements, or a political scientist analyzing historical colony formation, or a planetary scientist modeling in situ resource availability, you keep getting answers that cluster in the same general range. 100 to 300 years for genuine civilizational self-sufficiency, decades for the early milestones, generations for the meaningful ones. That consistency across such different approaches is actually a form of scientific evidence in itself. It suggests that the timeline isn't primarily a function of any one technical challenge. It isn't mainly about rocket propulsion or radiation shielding or food production or governance. It's about the cumulative interacting complexity of all of those challenges together and the time it takes for a human community to navigate that complexity while simultaneously maintaining its own continuity. But here's what I want to spend the rest of this part exploring, because we've been talking about timelines largely in terms of obstacles, in terms of what needs to be overcome, solved, engineered around, managed, survived. And that framing, while honest and necessary, misses something equally important. It misses what Mars might give back, not just as a refuge, not just as a backup civilization in case something goes catastrophically wrong on Earth, though that is a genuine and serious argument for colonization that Stephen Hawking, Elon Musk, and many planetary scientists have made publicly and forcefully, but as a place that actively enriches human knowledge and understanding in ways we cannot fully anticipate. Think about what happened scientifically when humans reached Antarctica. The discovery of the ozone hole, one of the most important environmental findings of the 20th century, came directly from atmospheric measurements taken at Antarctic research stations. The study of ice cores drilled from the Antarctic ice sheet has given us the most detailed record of Earth's climate history available anywhere on the planet, stretching back 800,000 years and providing essential data for understanding both past climate dynamics and future projections. The extremophile organisms discovered in Antarctic environments have transformed our understanding of the limits of life and dramatically expanded the range of environments we consider potentially habitable elsewhere in the universe. Antarctica is cold, hostile, and deeply inhospitable to human life. It is also one of the most scientifically productive environments on Earth. And Mars, with its record of ancient water flows, its preserved geological history stretching back 4 billion years, largely undisturbed by the plate tectonics that constantly recycles Earth's geological record, its potential subsurface environments where microbial life might persist even today, Mars is scientifically richer by orders of magnitude. The question of whether Mars ever harbored life and whether anything lives there now in protected subsurface niches is arguably the most important unanswered question in all of science, because the answer doesn't just tell us about Mars, it tells us about the universe. If life arose independently on Mars, even simple microbial life, even 3 billion years ago, then life is probably ubiquitous across the cosmos. The chemistry that produces it is not some extraordinary accident specific to one small world. It is a natural consequence of the basic physics and chemistry of the universe, playing out wherever conditions permit. And if Mars is sterile, if it never developed life despite having liquid water, chemical energy, and a reasonably hospitable early environment for hundreds of millions of years, then that too is enormously informative. It suggests that the emergence of life, even given the right conditions, is not inevitable, that the step from chemistry to biology is genuinely rare, that Earth's biosphere might be something extraordinary rather than something typical in a universe full of living worlds. Either answer is profound. Either answer reshapes our understanding of our place in the cosmos, and neither answer can be definitively obtained by remote sensing or robotic exploration alone. The subsurface environments where life, if it exists, would most likely persist on Mars today are accessible only through drilling and direct investigation, the kind of investigation that human explorers and scientists, working on the surface with the full flexibility of human perception and intelligence, are far better equipped to conduct than any robotic system currently conceivable. There's another gift that Mars might offer, and it's one that is rarely framed in these terms, but that I think deserves to be. The gift of perspective. When the first generation of Martian-born humans looks up at the night sky and finds Earth, a brilliant blue-white star, the third brightest object in the Martian sky after the Sun and the moon Phobos, they will see it differently from the way we see Mars. They will see it as home, as origin, as the source of everything their civilization carries within it. Every story, every mathematical framework, every piece of music, every ethical tradition, every scientific method, every language. And from that perspective, Earth will look different. The geopolitical divisions that seem so absolute from within will look smaller. The environmental crises that seem so local will look like what they actually are: threats to the only living world in our solar system other than their own. The philosophical and cultural diversity that sometimes seems like a source of conflict will look like richness, like the very thing that made their civilization resilient enough to survive the journey across interplanetary space. The Apollo astronauts described something like this: a shift in perspective that came from seeing Earth as a whole, from the outside, for the first time. Edgar Mitchell, who walked on the moon during Apollo 14 in 1971, described the experience as a sudden, overwhelming sense of interconnectedness, an understanding, felt rather than merely thought, that everything on that small blue world was part of a single living system. He spent the rest of his life trying to articulate and share that insight. The philosopher and cognitive scientist David Yarden at Johns Hopkins University has studied this phenomenon, which researchers call the overview effect, and found that it produces measurable, lasting changes in psychological well-being, in pro-social behavior, and in environmental concern. A significant fraction of astronauts report that the experience of seeing Earth from space changed their priorities and values in ways that persisted for years afterward. Now imagine that effect experienced not as a temporary visit, not as a brief glimpse from orbit or from the surface of the Moon, but as the permanent condition of an entire civilization living on another planet. What does a society look like when every person in it grows up seeing Earth as a distant light in the sky? When the overview effect is not a rare privileged experience, but the default condition of everyday life? We genuinely don't know. We can speculate, we can extrapolate from what we know about how physical environments shape cultures and worldviews, but the honest answer is that the second civilization to emerge from human biology, the Martian one, will think thoughts and hold values and build social structures that we, from our vantage point in 2026, cannot fully anticipate or imagine. And that, to me, is one of the most extraordinary things about the entire project. Not the engineering, not the biology, not even the timeline, but the fact that what we are really talking about when we talk seriously, honestly about colonizing Mars is the creation of a new kind of human experience, a new way of being alive in the universe, a new vantage point from which to ask the oldest questions. Why are we here? Where did we come from? Are we alone? Those questions don't get smaller when you ask them from Mars. They get larger, because from Mars you're asking them with the full weight of two worlds behind you and an entire galaxy ahead. Let's start with a thought experiment. Imagine you arrive on a planet that 4 billion years ago looked remarkably similar to early Earth. It had a thicker atmosphere. It had liquid water flowing across its surface, rivers, lakes, and possibly even a shallow ocean covering much of its northern hemisphere. It had a magnetic field shielding it from solar radiation. It had, in other words, many of the conditions that allowed life to emerge and flourish on our own world. Then something went wrong. The core cooled, the magnetic field collapsed, the atmosphere was stripped away, the water froze or escaped into space, and over hundreds of millions of years, a world that might have been alive became the frozen, irradiated, nearly airless desert we see today. Now imagine you have the technology, primitive, expensive, incomplete but real, to begin reversing that process, to warm the planet, to thicken its atmosphere, to coax liquid water back onto its surface, to, over centuries or millennia, restore something approaching the conditions Mars once naturally had. Would you do it? That question is not rhetorical. It is one of the most actively debated topics in planetary science and astrobiology today, and the answer, depending on which scientist you ask and what evidence they weight most heavily, ranges from absolutely, and we should start planning now, to we must not do this under any circumstances until we are completely certain we understand what we would be destroying. Let's start with the physics and chemistry, because before we get to the ethics, we need to understand whether terraforming Mars is even possible, and on what timescale, given the actual constraints of planetary science. The core challenge of terraforming Mars is straightforward to state and enormously difficult to solve. Mars is cold, average surface temperature around -60 degrees Celsius. Its atmosphere is thin, surface pressure roughly 1/600th of Earth's, and it receives less solar energy per square meter than Earth does. To make Mars habitable without spacesuits, you need to warm it by roughly 60 degrees Celsius on average, increase its atmospheric pressure by a factor of roughly 100, and introduce breathable levels of oxygen into that thickened atmosphere. That is a staggering amount of planetary engineering. But here's what makes it a serious scientific discussion rather than pure fantasy. Mars may actually contain the raw materials needed to begin this process. if you're willing to work on a timescale measured not in years or decades but in centuries. The most discussed first step in any serious terraforming proposal is warming Mars enough to trigger a runaway greenhouse effect using the planet's own resources. And the mechanism most seriously proposed involves the release of greenhouse gases currently frozen into the Martian polar ice caps and subsurface permafrost, primarily carbon dioxide, but potentially also other gases. Here's the physics. Mars's south polar cap contains a known reservoir of frozen carbon dioxide. If that frozen carbon dioxide could be vaporized and released into the atmosphere, it would begin to trap solar heat, warming the surface, which would in turn release more frozen carbon dioxide, which would trap more heat. A positive feedback loop that, if it could be triggered and sustained, might begin to genuinely alter the planetary climate. Carl Sagan himself was one of the earliest serious proponents of this concept, outlining it in a 1973 paper published in the journal Icarus. The basic physics he described has held up. The question is whether the available carbon dioxide reservoir is large enough to drive meaningful warming on its own, and more recent research has cast serious doubt on this. A landmark 2018 study published in Nature Astronomy, led by planetary scientist Bruce Jakosky of the University of Colorado Boulder, conducted a comprehensive inventory of all known carbon dioxide reservoirs on Mars. The polar caps, the regolith, subsurface deposits, minerals. The conclusion was sobering. Even if every accessible carbon dioxide reservoir on Mars were completely released into the atmosphere, the resulting atmospheric pressure increase would be roughly 1 to 2% of Earth's, far short of the levels required for liquid water stability or unprotected human habitation. Mars simply may not have enough accessible carbon dioxide to terraform itself through this mechanism alone. This finding significantly cooled, if you'll forgive the pun, the scientific community's enthusiasm for fast terraforming scenarios. The proposals that remain on the table after that 2018 paper are either much more technologically intensive, operating on much longer timescales, or both. One approach that has received serious attention involves manufacturing and releasing potent synthetic greenhouse gases into the Martian atmosphere. Compounds like perfluorocarbons, which are extraordinarily effective greenhouse gases, thousands of times more powerful per molecule than carbon dioxide at trapping heat, could, in theory, be produced using Martian resources and released in sufficient quantities to warm the planet significantly. A 2001 study by Margarita Marinova and colleagues at NASA Ames Research Center calculated that sustained production of specific perfluorocarbons at rates achievable by a sufficiently advanced industrial civilization on Mars could raise global temperatures by around 30 degrees Celsius over a period of roughly 100 years. 30 degrees in 100 years is genuinely significant. It would begin to thaw subsurface ice and permafrost. It would make liquid water stable in some equatorial regions. It would increase atmospheric pressure meaningfully, though still far short of what unprotected humans need. But here's the critical qualifier in every sentence of that paragraph. Sufficiently advanced industrial civilization, sustained production. These phrases are doing enormous amounts of work. The industrial capacity required to produce greenhouse gases at the quantities needed to move planetary atmospheric chemistry on Mars with no existing infrastructure, with a small initial population, with every manufacturing input either produced locally or shipped from 150 million kilometers away, is itself a multi-generational project. You can't begin serious terraforming before you have a serious colony. And you can't have a serious colony without first solving all the problems we've been discussing for the last 6 parts of this video. So terraforming, realistically, is not an alternative to the colonization timeline we've already mapped out. It's something that runs alongside it, beginning modestly during the settlement phase and scaling up gradually as the Martian civilization develops the industrial and technological capacity to pursue it meaningfully. The full timeline for even partial terraforming, bringing Mars to a state where liquid water is stable on the surface and the atmospheric pressure is perhaps 10 to 20% of Earth's, is estimated by most planetary scientists at somewhere between 300 and 1,000 years. Under optimistic assumptions about industrial capacity and technological development, full terraforming, an open, breathable atmosphere with temperatures and pressures fully compatible with unprotected human life, is, if possible at all, a project measured in thousands of years. Kim Stanley Robinson's fictional timeline of roughly 500 years for substantial terraforming is considered by most planetary scientists to be extremely optimistic. The more sober estimates cluster around 1,000 to 100,000 years, depending on the methods used and the resources available, 1,000 to 100,000 years. That's not a typo. That's the actual range that serious planetary scientists discuss when they're talking about full terraforming of Mars. The lower end of that range, 1,000 years, requires technologies and industrial scales that don't yet exist. The upper end involves processes that are essentially geological in their pace, slowly, molecule by molecule, rebuilding a planetary atmosphere. But here's where the ethical dimension enters and why it matters so profoundly for the colonization timeline and everything beyond it. If Mars is sterile, if there is no life there, has never been life there, and the planet is simply a vast repository of interesting chemistry and geology, then the ethical calculus of terraforming is relatively straightforward. You are not destroying anything that lives. You are transforming a dead world into a living one. The only serious ethical concern involves the scientific value of the pristine Martian environment, which would be irrevocably altered by terraforming. And while that concern is genuine, most researchers consider it manageable through careful scientific documentation and the preservation of protected zones. But what if Mars is not sterile? This is where the question becomes genuinely difficult. And the reason it's difficult is that we don't yet know the answer, and may not know definitively for decades. The evidence for potential present-day Martian life is circumstantial but not trivial. The discovery of methane in the Martian atmosphere, first detected by the Mars Express orbiter in 2003 and subsequently measured by the Curiosity rover with puzzling seasonal variations, is scientifically interesting because methane is rapidly destroyed by ultraviolet radiation on Mars's surface. For it to be present at all, something must be producing it recently. That something could be geological. Certain chemical reactions between water and certain rock types can produce methane abiotically, but it could also be biological. Methane is a common metabolic byproduct of certain types of microorganisms, methanogens, that thrive in anaerobic, chemically reduced environments, exactly the kind of environment that might exist in Mars's deep subsurface. The 2018 discovery of a potential subglacial liquid water lake beneath the south polar ice cap of Mars, announced by Roberto Orosei and colleagues in the journal Science and detected using the Marsis radar instrument on Mars Express, added another data point. If liquid water exists beneath the ice, kept liquid by the pressure of the overlying ice and by the presence of dissolved salts, then there exists a plausible environment for extant microbial life on Mars today. Not on the surface, where radiation and chemical conditions are too hostile, but underground, in the dark, in the cold, in the brine, exactly where terrestrial extremophiles, like those found in Antarctica's subglacial lakes, have shown life can persist. None of this is proof. The methane observations have been contested and debated actively in the scientific literature. The subglacial lake interpretation of the Mars's data has been questioned by subsequent analyses. The scientific community is genuinely actively uncertain about whether Mars harbors life. But here is the profound ethical point that planetary protection researchers like Catherine Conley, who served as NASA's Planetary Protection Officer from 2006 to 2017, have been making for years. If there is any meaningful probability that Mars hosts its indigenous microbial life, then the question of whether to terraform it is not primarily a technical question. It is a moral one, of the deepest kind, because terraforming Mars, warming it, thickening its atmosphere, introducing Earth organisms to begin building a biosphere, would, almost certainly, be lethal to any indigenous Martian life, not intentionally, not through malice, but through the simple, inexorable process of ecological replacement that has played out on Earth every time a dominant species colonized a new environment. Earth organisms, optimized by billions of years of evolution for efficient resource use and rapid reproduction, would almost certainly outcompete any Martian microbes that had spent billions of years adapting to the cold, radiation-exposed, resource-scarce conditions of their native environment. We would be, potentially, committing the first act of interplanetary ecological destruction, the elimination of an entire independent origin of life, something that, as far as we know, has never happened before in the history of the universe, the deliberate or accidental extinction of life that arose completely independently of Earth's biology. The philosopher Christopher McKay has proposed what he calls the life-first principle for Mars, the idea that if life exists there, it has an intrinsic right to its own evolutionary future, and that human activity on Mars should be structured to protect rather than threaten it. He has argued, counterintuitively, that if Mars has indigenous life, terraforming should actually be accelerated, but only in ways that would benefit Martian life rather than Earth life, creating conditions where Martian organisms could thrive and spread rather than being displaced by terrestrial colonists. Other researchers, including Robert Zubrin of the Mars Society, have argued that we should not allow the possibility, not the certainty, but the mere possibility of Martian microbial life to indefinitely delay human colonization. That the potential benefit to one very complex, very intelligent, very creative species significantly outweighs the potential harm to microbial organisms that, however scientifically precious, do not have the kind of inner life that generates moral weight. These are not easy arguments to adjudicate. They involve deep questions about what gives life moral value. Is it complexity? Sentience? The mere fact of being alive? The rarity of an independent origin? Philosophers, ethicists, astrobiologists, and planetary scientists are actively arguing about all of these questions right now, in academic journals and conference rooms and late-night conversations over coffee, and there is no consensus. What there is consensus on is this: we need to answer the question of whether Mars has life before we make irreversible decisions about its future. And answering that question definitively, drilling deep enough, sampling broadly enough, exploring thoroughly enough to say with genuine confidence that Mars is or isn't biologically active, is itself a project that could take decades of robotic exploration followed by human scientific investigation on the surface. Which means that the ethical questions around terraforming are not just philosophical exercises for the distant future. They are practical constraints on the colonization timeline right now, because the decisions we make in the next few decades about planetary protection, about how carefully we sterilize our spacecraft, how cautiously we approach potential life-bearing environments, how thoroughly we investigate before we intervene, will determine whether we arrive at Mars as responsible explorers or as accidental destroyers. And here's what I find most moving about this entire dimension of the Mars question: the fact that we are even asking it, that we are, as a species, capable of looking at another world and asking not just, can we use this, but does this world have rights? Does life on Mars, if it exists, have a claim on its own future that we are obligated to respect? That capacity for moral consideration beyond our immediate self-interest is, arguably, one of the most remarkable things about human consciousness. It is the same capacity that eventually led us to recognize the rights of other human cultures, of other animal species, of ecosystems and natural environments on our own planet. The process has been slow and deeply imperfect. We have caused enormous harm before developing the wisdom to recognize and limit it. But the direction of travel toward expanding circles of moral consideration is unmistakable over the long arc of human ethical development, taking that expanding circle of moral consideration to Mars, asking, before we act, whether our actions could harm something precious, is not weakness, it is not timidity, it is the most human thing about this entire endeavor. It is what separates the colonization of Mars from every previous colonial project in human history. Those projects, almost without exception, began without moral consideration for what was already there. The Mars colonization project, if it's done right, can be the first great human expansion that begins with that question built into its foundations. Whether it will be done right is another matter entirely. And that brings us back, inevitably, to the question of political will, international cooperation, and the kinds of decisions that will be made in the next 20 to 30 years that will determine the shape of everything that follows. Because we are, right now, in the window that matters most. The decisions being made today about planetary protection protocols, about international space law, about how to structure the governance of Mars exploration before any permanent presence exists, are the decisions that will be hardest to reverse later. Legal frameworks, once established, develop constituencies and inertia. Precedents, once set, shape everything that follows. The period between approximately now and approximately 2050 is, by almost any analysis, the most consequential window in the entire Mars colonization story. It's the window in which the first human missions will be planned, funded, launched, and either succeed or fail. It's the window in which the basic legal and governance architecture for human activity on Mars will be sketched out, imperfectly, incompletely, but with lasting consequences. It's the window in which the scientific question of Martian life will be pursued with the most urgency and the most resources, because the answer matters most before human activity on the surface makes it impossible to answer cleanly, and it's the window in which you, yes, specifically you, watching this video, are alive, are paying attention, are capable of engaging with these questions, sharing them with other people, demanding that the institutions and governments and companies making these decisions do so with the care and the seriousness and the moral weight they deserve. The colonization of Mars is not just a story about engineers and astronauts and billionaires with rockets. It is a story about what kind of civilization humanity chooses to be at the moment it first reaches beyond its home world, and that choice is being made right now. Not in a single dramatic moment, but in thousands of small decisions, policy choices, funding priorities, and cultural conversations happening every day. If you are still watching, then this channel was created specifically for you. Don't forget to subscribe and give this video a like. You will be part of a community that explores the cosmos together. Right now, at this very moment, there is a 6-wheeled robot the size of a small car crawling across the floor of Jezero crater on Mars. It has been there since February 18th, 2021. It moves slowly at a maximum speed of roughly 0.15 kilometers per hour, and it stops frequently to drill into rocks, analyze their chemistry, and seal samples into small titanium tubes that it leaves behind on the surface in carefully mapped caches. Its name is Perseverance. And what it is doing, methodically and patiently in the cold Martian dust, is arguably the most important scientific work being conducted anywhere in the solar system right now. Jezero Crater was chosen as Perseverance's landing site for a specific and compelling reason. Orbital imagery and spectral analysis conducted by the Mars Reconnaissance Orbiter revealed that Jezero was once, approximately 3.5 to 3.9 billion years ago, a lake, not a temporary puddle, a genuine lake fed by an ancient river delta that deposited sediments rich in carbonates and other minerals, precisely the kinds of minerals that on Earth preserve biosignatures, the chemical traces of life, with extraordinary fidelity across geological timescales. If microbial life ever existed on Mars, Jezero Crater is one of the most likely places on the entire planet to have preserved evidence of it, and Perseverance has been collecting samples from exactly the kinds of geological contexts: ancient lake sediments, river delta deposits, igneous rocks that record the history of Mars's volcanic and hydrothermal activity that astrobiologists most want to examine. As of 2026, the rover has collected and sealed dozens of sample tubes, representing the most carefully selected and scientifically prioritized collection of Martian material ever assembled. But here's the thing that most people don't fully appreciate about what Perseverance is doing. Those samples are not being analyzed on Mars. They can't be. The instruments needed to definitively identify biosignatures require laboratory conditions that no rover can carry. Those samples are being stored, waiting for a mission that will come and collect them and bring them back to Earth, where scientists in actual laboratories with the full suite of analytical tools available to modern chemistry and biology will examine them for the most consequential discovery in the history of science. That mission is called Mars Sample Return, and its story in 2026 is one of the most important and most complicated chapters in the entire history of Mars exploration. Mars Sample Return was until recently one of the highest priority objectives in planetary science, ranked at the top of the National Academies of Sciences Planetary Science Decadal Survey, the document that sets the scientific priorities for NASA's planetary exploration program across a 10-year period. The joint NASA and European Space Agency mission architecture called for a sample retrieval lander to land near Perseverance's sample caches, deploy a small fetch rover to collect the tubes, launch them into Mars orbit on a Mars ascent vehicle, the first rocket ever launched from the surface of Mars, and rendezvous with an Earth return orbiter that would bring the samples safely back to Earth. The science case for this mission is as strong as it gets in planetary exploration. The engineering challenges are significant but tractable, and the potential return, the definitive answer to whether Mars ever hosted life, plus an unprecedented window into the geological and climate history of an entire planet, would transform our understanding of the solar system and of life's place within it. And then came the budget numbers. Independent cost assessments conducted in 2023 estimated the full Mars sample return mission at somewhere between $8 and $11 billion, more than 3 times NASA's original estimates. The development timeline had stretched from an original target of samples returning to Earth around 2031 to projections of 2038 or later. In response, NASA initiated a fundamental redesign of the mission architecture in 2024, seeking less expensive and faster alternatives that could still achieve the core scientific objective. As of 2026, that redesign process is ongoing. Several alternative architectures are being evaluated, including the possibility of using commercial launch providers, simplifying the orbital rendezvous sequence or breaking the mission into smaller components that can be developed on faster and cheaper timescales. The scientific community has watched this process with intense interest and, in some quarters, significant anxiety, because every year of delay in returning those samples is a year in which the most important scientific question about Mars goes unanswered. The Mars sample return story is, in microcosm, the story of the entire Mars program. Extraordinary science, extraordinary ambition, real engineering capability, and then the collision with budget realities, institutional complexity, and the grinding difficulty of doing genuinely unprecedented things within the constraints of democratic political systems, where funding priorities change with every election cycle. Meanwhile, SpaceX's Starship program has continued its own extraordinary and turbulent development trajectory. For those who haven't been following closely, and the pace of development has been fast enough that even dedicated followers struggle to keep up, let's map where things actually stand. Starship is a two-stage, fully reusable launch system consisting of the Super Heavy booster and the Starship upper stage. When fully stacked, it stands roughly 121 meters tall, taller than the Saturn V rocket that carried Apollo astronauts to the moon. It is powered by dozens of Raptor engines burning liquid methane and liquid oxygen, propellants that critically can be manufactured from carbon dioxide and water using the Sabatier reaction, meaning they could theoretically be produced on Mars from local resources. The first integrated flight test of the full Starship stack in April 2023 ended in a dramatic explosion several minutes after launch. The second test in November 2023 achieved a successful stage separation before both vehicles were lost. The third test, in March 2024, achieved the first successful re-entry of the Starship upper stage and a controlled splashdown of the Super Heavy booster. The fourth test, in June 2024, achieved the first successful catch of the Super Heavy booster by the launch tower's mechanical arms, a genuinely remarkable engineering achievement that, if it proves reliable, could dramatically reduce turnaround time between launches. Each test has demonstrated both SpaceX's remarkable capacity for rapid iteration and the genuine difficulty of the engineering challenges involved. Starship is not yet operational. It has not yet carried a payload to orbit. It has not yet demonstrated the in-orbit propellant transfer capability that Mars missions will require, a technically demanding operation involving docking two Starships in orbit and transferring cryogenic propellant between them, which has never been done before. And it has not yet demonstrated the autonomous surface landing capability on another world that any Mars mission will demand. Each of those remaining milestones is significant. Each involves engineering challenges that are real, not trivial, and the timeline from demonstrated promising test flights to launched first human Mars mission involves clearing every one of those hurdles reliably and repeatedly with human lives on the line. That said, and this is important, SpaceX has earned the right to be taken seriously in a way that no private aerospace company had before it. The development of the Falcon 9 rocket, the demonstration of first-stage booster reusability, the development of the Dragon spacecraft for crewed missions to the International Space Station. These are genuine achievements that would have seemed implausible predictions 20 years ago. The culture of rapid iteration, high tolerance for failure in testing, and aggressive timeline compression that SpaceX operates under has produced results that the more cautious pace of traditional aerospace development had not. So when the question is whether Starship will eventually work, whether it will become the reliable, reusable, Mars-capable launch system that its design intends, most aerospace engineers will tell you yes, probably. The question is when, and when is being answered in real time, test by test, iteration by iteration, with an honesty enforced by physics that no press release can override. On the other side of the geopolitical ledger, China's Mars ambitions deserve serious attention. More than they typically receive in Western coverage of the space race, China's Tianwen-1 mission, launched in July 2020 and arriving at Mars in February 2021, successfully deployed the Zhurong rover onto the Utopia Planitia region of Mars, making China only the second country in history, after the United States, to successfully operate a rover on the Martian surface. The mission returned significant scientific data about the geological structure and subsurface water ice distribution in its landing region, contributing meaningfully to the global picture of Martian science. China has publicly stated its intention to conduct a Mars sample return mission of its own, with an ambitious target of returning samples to Earth around 2031, ahead of NASA's current projected timeline for its own sample return mission. Whether that timeline proves achievable is an open question, given the enormous engineering complexity involved. But the intent is clear, the funding is being committed, and the technical capability demonstrated by Tianwen-1 suggests this should not be dismissed. More broadly, China's national space program, funded by the world's second-largest economy, staffed by an extraordinarily large and rapidly developing engineering and scientific workforce, and operating within a political system that can commit to long-term programs without the budget uncertainty that plagues democratic space agencies, represents a genuinely competitive force in the exploration and eventual utilization of Mars. Whether that competition ultimately accelerates or complicates the path to human Mars colonization is one of the most consequential open questions in contemporary space policy. The history of space exploration suggests that competition, while sometimes wasteful, is also a powerful motivator. The Apollo program happened because the Soviet Union appeared to be winning the space race. Political urgency, not scientific curiosity alone, drove the extraordinary mobilization of resources that put humans on the Moon in 8 years. If a perceived Chinese lead in Mars exploration generates similar political urgency in the United States and its allies, the effect on the timeline could be significant. India's space program is also increasingly relevant to this conversation. The Indian Space Research Organization's Mangalyaan mission, also known as Mars Orbiter mission, successfully entered Mars orbit in September 2014, making India the first Asian nation and the first in the world to succeed on its first attempt. India has announced plans for a follow-up Mars mission, and its Chandrayaan lunar program has demonstrated growing sophistication in deep space mission design and execution. India's eventual role in Mars exploration, whether through its own missions, through partnerships with NASA or ESA, or through commercial collaboration with SpaceX, adds another dimension to an already complex international picture. The robotic missions currently operating at Mars, and those in various stages of development and planning, are not just scientific endeavors in isolation from the human colonization question. They are, collectively, building the knowledge base that human missions will depend on. Every meter of terrain mapped by orbiters refines our understanding of where safe landing sites exist, where resources are accessible, where the most scientifically valuable and potentially life-bearing environments are located. Every measurement taken by surface rovers adds to the engineering data that habitat and life support designers need. Every atmospheric observation informs the models that mission planners use to understand dust storm risk, thermal cycling, and the engineering environment that surface systems will face. The science and the exploration are not separate from the colonization project. They are its foundation, and the pace at which that foundation is being built, despite budget pressures, despite geopolitical complications, despite the grinding difficulty of operating machinery on another planet from 150 million kilometers away, is genuinely remarkable when you step back and look at it clearly. Consider the fact that as of 2026, we have been continuously operating spacecraft in Mars orbit for over 25 years. Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, MAVEN, Mars Orbiter Mission, Trace Gas Orbiter, Hope, Tianwen-1's Orbiter, a succession of human-built machines working alone in the cold dark of Martian orbit, relaying data back to teams of scientists on Earth who have built careers and lifetimes around understanding this planet. That is an extraordinary sustained commitment maintained across multiple decades, multiple governments, multiple generations of scientists and engineers, and on the surface, Curiosity, now well past its original planned mission duration of 1 Martian year, roughly 687 Earth days, continues to operate in Gale Crater, its nuclear power source still generating enough electricity to run its instruments, still climbing the sedimentary layers of Mount Sharp and reading the ancient climate history of Mars encoded in its rocks. Perseverance, newer and more capable, is doing the same in Jezero. 2 rovers simultaneously building a picture of Mars that would have been unimaginable to the scientists who first pointed telescopes at that reddish point of light in the night sky. But here's what all of this activity, the rovers, the orbiters, the sample collection, the launch vehicle development, the international competition and collaboration converges toward. A moment that is, depending on how the next decade unfolds, somewhere between 5 and 15 years away. The moment when a human being, for the first time in the 4.6 billion year history of this solar system, sets foot on a world other than the one they were born on, not the moon. That happened. A world that took months to reach, a world with no return ticket waiting for you in orbit. A world where the environment will kill you within minutes if your equipment fails, where the nearest help is a light travel time of up to 22 minutes away, and where every decision you make carries consequences that no amount of simulation or training can fully prepare you for. The people who will do that, who will climb down a ladder, step onto Martian regolith, and become the first humans in history to stand on another planet, are almost certainly alive today. They might be in their 20s or 30s. They might be military pilots or scientists or engineers or some combination of all three. They might be American or Chinese or some other nationality entirely. They probably don't know yet that it will be them, though some of them may suspect. What will they feel? Standing there, what will they see? The Martian sky at noon on a clear day near the equator is not the dramatic red that popular culture has painted. It is closer to butterscotch, a pale, dusty tan scattered by fine mineral particles suspended in the thin atmosphere. The Sun, from Mars, appears roughly 2/3 the size it does from Earth, noticeably smaller, distinctly less warm. The horizon is closer than on Earth because Mars is a smaller planet. The landscape, in regions like Jezero or Gale, looks startlingly familiar in some ways. Rocky, sculpted by ancient water and wind, layered with the geological history of billions of years, and utterly alien in others. They will be wearing spacesuits. Their movement will be constrained. Their senses partially insulated from the environment around them. But they will be there, actually there, and in that moment something will shift in the human story that cannot be unshifted. We will have become a 2-planet species, tentatively, temporarily, incompletely, but genuinely right now, at this very moment, there is a 6-wheeled robot the size of a small car crawling across the floor of Jezero crater on Mars. It has been there since February 18th, 2021. It moves slowly, at a maximum speed of roughly 0.15 kilometers per hour, and it stops frequently to drill into rocks, analyze their chemistry, and seal samples into small titanium tubes that it leaves behind on the surface in carefully mapped caches. Its name is Perseverance, and what it is doing methodically and patiently in the cold Martian dust is arguably the most important scientific work being conducted anywhere in the solar system right now. Jezero Crater was chosen as Perseverance's landing site for a specific and compelling reason. Orbital imagery and spectral analysis conducted by the Mars Reconnaissance Orbiter revealed that Jezero was once, approximately 3.5 to 3.9 billion years ago, a lake, not a temporary puddle. A genuine lake fed by an ancient river delta that deposited sediments rich in carbonates and other minerals, precisely the kinds of minerals that, on Earth, preserve biosignatures, the chemical traces of life, with extraordinary fidelity across geological timescales. If microbial life ever existed on Mars, Jezero Crater is one of the most likely places on the entire planet to have preserved evidence of it. And Perseverance has been collecting samples from exactly the kinds of geological contexts, ancient lake sediments, river delta deposits, igneous rocks that record the history of Mars's volcanic and hydrothermal activity that astrobiologists most want to examine. As of 2026, the rover has collected and sealed dozens of sample tubes, representing the most carefully selected and scientifically prioritized collection of Martian material ever assembled. But here's the thing that most people don't fully appreciate about what Perseverance is doing. Those samples are not being analyzed on Mars. They can't be. The instruments needed to definitively identify biosignatures require laboratory conditions that no rover can carry. Those samples are being stored, waiting for a mission that will come and collect them and bring them back to Earth, where scientists in actual laboratories, with the full suite of analytical tools available to modern chemistry and biology, will examine them for the most consequential discovery in the history of science. That mission is called Mars Sample Return, and its story in 2026 is one of the most important and most complicated chapters in the entire history of Mars exploration. Mars Sample Return was, until recently, one of the highest priority objectives in planetary science, ranked at the top of the National Academies of Sciences Planetary Science Decadal Survey, the document that sets the scientific priorities for NASA's planetary exploration program across a 10-year period. The joint NASA and European Space Agency mission architecture called for a sample retrieval lander to land near Perseverance's sample caches, deploy a small fetch rover to collect the tubes, launch them into Mars orbit on a Mars ascent vehicle, the first rocket ever launched from the surface of Mars, and rendezvous with an Earth return orbiter that would bring the samples safely back to Earth. The science case for this mission is as strong as it gets in planetary exploration. The engineering challenges are significant but tractable, and the potential return, the definitive answer to whether Mars ever hosted life, plus an unprecedented window into the geological and climate history of an entire planet, would transform our understanding of the solar system and of life's place within it. And then came the budget numbers. Independent cost assessments conducted in 2023 estimated the full Mars sample return mission at somewhere between $8 and $11 billion, more than 3 times NASA's original estimates. The development timeline had stretched from an original target of samples returning to Earth around 2031 to projections of 2038 or later. In response, NASA initiated a fundamental redesign of the mission architecture in 2024, seeking less expensive and faster alternatives that could still achieve the core scientific objective. As of 2026, that redesign process is ongoing. Several alternative architectures are being evaluated, including the possibility of using commercial launch providers, simplifying the orbital rendezvous sequence, or breaking the mission into smaller components that can be developed on faster and cheaper timescales. The scientific community has watched this process with intense interest and, in some quarters, significant anxiety, because every year of delay in returning those samples is a year in which the most important scientific question about Mars goes unanswered. The Mars sample return story is, in microcosm, the story of the entire Mars program. Extraordinary science, extraordinary ambition, real engineering capability, and then the collision with budget realities, institutional complexity, and the grinding difficulty of doing genuinely unprecedented things within the constraints of democratic political systems where funding priorities change with every election cycle. Meanwhile, SpaceX's Starship program has continued its own extraordinary and turbulent development trajectory. For those who haven't been following closely, and the pace of development has been fast enough that even dedicated followers struggle to keep up. Let's map where things actually stand. Starship is a two-stage, fully reusable launch system consisting of the Super Heavy booster and the Starship upper stage. When fully stacked, it stands roughly 121 meters tall, taller than the Saturn V rocket that carried Apollo astronauts to the Moon. It is powered by dozens of Raptor engines burning liquid methane and liquid oxygen, propellants that critically can be manufactured from carbon dioxide and water using the Sabatier reaction, meaning they could theoretically be produced on Mars from local resources. The first integrated flight test of the full Starship stack in April 2023 ended in a dramatic explosion several minutes after launch. The second test in November 2023 achieved a successful stage separation before both vehicles were lost. The third test, in March 2024, achieved the first successful re-entry of the Starship upper stage and a controlled splashdown of the Super Heavy booster. The fourth test in June 2024 achieved the first successful catch of the Super Heavy booster by the launch tower's mechanical arms. A genuinely remarkable engineering achievement that, if it proves reliable, could dramatically reduce turnaround time between launches. Each test has demonstrated both SpaceX's remarkable capacity for rapid iteration and the genuine difficulty of the engineering challenges involved. Starship is not yet operational. It has not yet carried a payload to orbit. It has not yet demonstrated the in-orbit propellant transfer capability that Mars missions will require. A technically demanding operation involving docking two starships in orbit and transferring cryogenic propellant between them, which has never been done before, and it has not yet demonstrated the autonomous surface landing capability on another world that any Mars mission will demand. Each of those remaining milestones is significant. Each involves engineering challenges that are real, not trivial, and the timeline from demonstrated promising test flights to launched first human Mars mission involves clearing every one of those hurdles, reliably and repeatedly, with human lives on the line. That said, and this is important, SpaceX has earned the right to be taken seriously in a way that no private aerospace company had before it. The development of the Falcon 9 rocket, the demonstration of first-stage booster reusability, the development of the Dragon spacecraft for crewed missions to the International Space Station, these are genuine achievements that would have seemed implausible predictions 20 years ago. The culture of rapid iteration, high tolerance for failure in testing, and aggressive timeline compression that SpaceX operates under has produced results that the more cautious pace of traditional aerospace development had not. So when the question is whether Starship will eventually work, whether it will become the reliable, reusable, Mars-capable launch system that its design intends, most aerospace engineers will tell you yes, probably. The question is when, and when is being answered in real time, test by test, iteration by iteration, with an honesty enforced by physics that no press release can override. On the other side of the geopolitical ledger, China's Mars ambitions deserve serious attention, more than they typically receive in Western coverage of the space race. China's Tianwen-1 mission, launched in July 2020 and arriving at Mars in February 2021, successfully deployed the Zhurong rover onto the Utopia Planitia region of Mars, making China only the second country in history, after the United States, to successfully operate a rover on the Martian surface. The mission returned significant scientific data about the geological structure and subsurface water ice distribution in its landing region, contributing meaningfully to the global picture of Martian science. China has publicly stated its intention to conduct a Mars sample return mission of its own, with an ambitious target of returning samples to Earth around 2031, ahead of NASA's current projected timeline for its own sample return mission. Whether that timeline proves achievable is an open question, given the enormous engineering complexity involved, but the intent is clear, the funding is being committed, and the technical capability demonstrated by Tianwen-1 suggests this should not be dismissed. More broadly, China's national space program, funded by the world's second-largest economy, staffed by an extraordinarily large and rapidly developing engineering and scientific workforce, and operating within a political system that can commit to long-term programs without the budget uncertainty that plagues democratic space agencies, represents a genuinely competitive force in the exploration and eventual utilization of Mars. Whether that competition ultimately accelerates or complicates the path to human Mars colonization is one of the most consequential open questions in contemporary space policy. The history of space exploration suggests that competition, while sometimes wasteful, is also a powerful motivator. The Apollo program happened because the Soviet Union appeared to be winning the space race. Political urgency, not scientific curiosity alone, drove the extraordinary mobilization of resources that put humans on the Moon in 8 years. If a perceived Chinese lead in Mars exploration generates similar political urgency in the United States and its allies, the effect on the timeline could be significant. India's space program is also increasingly relevant to this conversation. The Indian Space Research Organization's Mangalyaan mission, also known as Mars Orbiter mission, successfully entered Mars orbit in September 2014, making India the first Asian nation and the first in the world to succeed on its first attempt. India has announced plans for a follow-up Mars mission, and its Chandrayaan lunar program has demonstrated growing sophistication in deep space mission design and execution. India's eventual role in Mars exploration, whether through its own missions, through partnerships with NASA or ESA, or through commercial collaboration with SpaceX, adds another dimension to an already complex international picture. The robotic missions currently operating at Mars, and those in various stages of development and planning, are not just scientific endeavors in isolation from the human colonization question. They are, collectively, building the knowledge base that human missions will depend on. Every meter of terrain mapped by orbiters refines our understanding of where safe landing sites exist, where resources are accessible, where the most scientifically valuable and potentially life-bearing environments are located. Every measurement taken by surface rovers adds to the engineering data that habitat and life support designers need. Every atmospheric observation informs the models that mission planners use to understand dust source risk, thermal cycling, and the engineering environment that surface systems will face. The science and the exploration are not separate from the colonization project. They are its foundation, and the pace at which that foundation is being built, despite budget pressures, despite geopolitical complications, despite the grinding difficulty of operating machinery on another planet from 150 million kilometers away, is genuinely remarkable when you step back and look at it clearly. Consider the fact that as of 2026, we have been continuously operating spacecraft in Mars orbit for over 25 years. Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, MAVEN, Mars Orbiter Mission, Trace Gas Orbiter, Hope Tianwen-1's Orbiter, a succession of human-built machines working alone in the cold dark of Martian orbit, relaying data back to teams of scientists on Earth who have built careers and lifetimes around understanding this planet. That is an extraordinary, sustained commitment maintained across multiple decades, multiple governments, multiple generations of scientists and engineers. And on the surface, Curiosity, now well past its original planned mission duration of 1 Martian year, roughly 687 Earth days, continues to operate in Gale Crater, its nuclear power source still generating enough electricity to run its instruments, still climbing the sedimentary layers of Mount Sharp and reading the ancient climate history of Mars encoded in its rocks. Perseverance, newer and more capable, is doing the same in Jezero, 2 rovers simultaneously building a picture of Mars that would have been unimaginable to the scientists who first pointed telescopes at that reddish point of light in the night sky. But here's what all of this activity, the rovers, the orbiters, the sample collection, the launch vehicle development, the international competition and collaboration converges toward. A moment that is, depending on how the next decade unfolds, somewhere between 5 and 15 years away. The moment when a human being, for the first time in the 4.6 billion-year history of this solar system, sets foot on a world other than the one they were born on, not the moon. That happened. A world that took months to reach. A world with no return ticket waiting for you in orbit. A world where the environment will kill you within minutes if your equipment fails, where the nearest help is a light travel time of up to 22 minutes away, and where every decision you make carries consequences that no amount of simulation or training can fully prepare you for. The people who will do that, who will climb down a ladder, step onto Martian regolith, and become the first humans in history to stand on another planet, are almost certainly alive today. They might be in their 20s or 30s, they might be military pilots or scientists or engineers, or some combination of all three. They might be American or Chinese or some other nationality entirely. They probably don't know yet that it will be them, though some of them may suspect. What will they feel standing there? What will they see? The Martian sky at noon on a clear day near the equator is not the dramatic red that popular culture has painted. It is closer to butterscotch, a pale, dusty tan, scattered by fine mineral particles suspended in the thin atmosphere. The Sun, from Mars, appears roughly 2/3 the size it does from Earth, noticeably smaller, distinctly less warm. The horizon is closer than on Earth because Mars is a smaller planet. The landscape in regions like Jezero or Gale looks startlingly familiar in some ways, rocky, sculpted by ancient water and wind, layered with the geological history of billions of years, and utterly alien in others. They will be wearing spacesuits. Their movement will be constrained, their senses partially insulated from the environment around them, but they will be there, actually there, and in that moment, something will shift in the human story that cannot be unshifted. We will have become a 2-planet species, tentatively, temporarily, incompletely, but genuinely. And that moment, as extraordinary as it will be, is just the first step of the journey we've been mapping across this entire video. The step that leads, over decades and generations and centuries, through all the challenges and all the sacrifices and all the extraordinary human creativity and determination that will be required, towards something that has never existed before, a second home. We are almost at the end of this story. This is where we bring all of the timelines, all of the science, all of the human dimensions together into the clearest, most honest answer we can give to the question that started all of this: how long would it really take? The answer, when you lay all the evidence on the table, is both more complicated and more beautiful than a single number can capture. There's a concept in complexity science called an emergent property. It describes something that arises from the interaction of many simpler components, something that couldn't have been predicted by studying any one of those components in isolation. Water is wet, but neither hydrogen nor oxygen alone is wet. Consciousness emerges from neurons, but no single neuron is conscious. Traffic jams emerge from individual driving decisions, but no single driver intends to create one. The colonization of Mars is an emergent property of civilization. It cannot be reduced to any single technology, any single mission, any single political decision, or any single scientific breakthrough. It arises slowly, messily, unpredictably, from the interaction of thousands of developments across dozens of fields, driven by millions of individual decisions made by scientists, engineers, politicians, investors, explorers, and ordinary people who look up at the night sky and feel something they can't quite name pulling them toward the stars. And that means the timeline for colonizing Mars is not a fixed number sitting somewhere in the future, waiting to be discovered. It is being actively shaped right now by the decisions being made today, which means the answer to how long would it really take depends in part on what we choose to do about it, on what we collectively decide this project is worth, on whether we treat it as a distant abstraction or as the most important long-term project our civilization has ever undertaken. That's not a motivational flourish to close out the video. It's a direct implication of everything the science tells us. So let's lay it all out, clearly and honestly, one final time. Here is the most accurate, evidence-based timeline for Mars colonization that the current state of science supports. Not the optimistic version, not the pessimistic version. The honest version with appropriate uncertainty ranges, built from the research we've discussed across every part of this video. The first human landing on Mars, somewhere between 2028 and 2038. The lower end of that range requires SpaceX's Starship to perform at or near its designed capability within the next few years, sustained political and financial commitment from the relevant governments, and no major mission-ending failures during the critical development and validation phase. The upper end reflects the historical reality that new human spaceflight systems consistently take longer to develop than initially projected, and that the gap between a promising test program and an operational crewed vehicle is almost always larger than it looks from the outside. The most likely single year for the first human Mars landing, if you forced every serious aerospace analyst to give one number, would probably cluster somewhere around 2033 to 2035. That's not a prediction. It's a central tendency in a distribution of possibilities that stretches from the late 2020s to the early 2040s, the first permanent, continuously occupied Mars outpost. Approximately 10 to 20 years after the first human landing, so somewhere between 2045 and 2055, under moderately optimistic assumptions. This milestone requires not just getting humans to Mars, but building the habitat infrastructure, life support systems, food production capacity, and power generation that can sustain a rotating crew indefinitely through Martian dust storms, equipment failures, medical emergencies, and the full range of operational stresses that only reveal themselves once you're actually there and living it. The first Mars settlement with genuine community characteristics, children born there, cultural institutions developing, a population that considers Mars home rather than a deployment. is perhaps another 20 to 30 years beyond that. Call it late 21st century. Somewhere between 2070 and 2090, if the outpost phase goes reasonably well and the population pipeline from Earth is sustained across multiple decades. Early self-sufficiency, the ability to survive a missed resupply window without immediate catastrophe, follows the settlement-made phase by perhaps another decade to 2 decades. So roughly late 21st century to early 22nd century, around 2090 to 2110, full civilizational self-sufficiency, the ability to survive permanently without Earth's support, with a population large enough to be genetically viable, a technological base capable of reproducing its own critical systems across generations, and a social and governance structure mature enough to manage internal conflict without external arbitration, is the milestone that most researchers refuse to put a precise date on because the uncertainty is simply too large. The range that comes up most consistently in the serious literature is 100 to 300 years after the establishment of the first permanent outpost, which, chaining the timelines together, means somewhere between the 22nd and the 24th century. Write it out plainly. The honest answer to how long would it really take to colonize Mars, using the definition of colonization that actually means something, the definition that means a self-sustaining human civilization capable of persisting indefinitely on another world, is somewhere between 150 and 350 years from now. Not a decade, not a generation, centuries now. Before anyone interprets that as a counsel of despair, let me offer a reframe that I think is both scientifically honest and genuinely important. 1.5 centuries to 3.5 centuries is a long time on a human scale. It is not a long time on any other scale that matters when you're talking about planetary civilization. The Roman Empire, from its founding as a republic to the fall of its western half, spanned roughly 1,000 years. The agricultural revolution that allowed the first human cities to exist began 12,000 years ago and is still unfolding. The scientific revolution, the single most transformative shift in human knowledge and capability in our species' history, has been building for roughly 400 years and shows no sign of plateauing. The colonization of Mars on those scales is not a distant fantasy. It is an immediate next chapter. It is the thing that happens in the blink of a cosmic eye, building on 4 billion years of biological evolution and 10,000 years of cultural development. We are not waiting for the far future. We are standing at its doorway. And there's something else. The timeline is not fixed. It is elastic. It responds to the inputs we give it. Consider what could shorten it. A breakthrough in propulsion technology, nuclear thermal, nuclear pulse, or some form of advanced electric propulsion that cuts transit times to Mars from 6 to 9 months to perhaps 4 to 6 weeks. That single change would transform every aspect of the colonization equation. More frequent missions, far less radiation exposure for crews, greater flexibility in launch windows, a supply chain that looks more like a brisk maritime trade route than a months-long ocean crossing. Is such a breakthrough possible within decades? The physics doesn't forbid it. Nuclear pulse propulsion, the concept explored seriously under Project Orion in the 1950s and 60s, could theoretically achieve transit times measured in weeks rather than months, using the pressure of sequential nuclear explosions as a propulsive force. The engineering, political, and treaty challenges of that approach are enormous, but the physics works. Advanced nuclear fusion propulsion, still the perpetual 30 years away technology of popular frustration, but genuinely advancing through programs like the National Ignition Facility's inertial confinement work and private companies like Helion Energy pursuing compact fusion reactors, could, if it matures, provide propulsion capabilities that make the current Starship architecture look like a dugout canoe compared to a container ship, or consider what breakthroughs in biology and medicine could do to the timeline. If we develop reliable countermeasures for the bone density loss, muscle atrophy, cardiovascular deconditioning, and neurological effects of long-duration spaceflight, pharmaceutical, genetic, or technological, then the human body becomes a much less limiting factor. If we develop radiation-protective pharmaceuticals that can be taken prophylactically, and there is genuine, serious research happening in this area right now at institutions like the NASA Human Research Program, then the 6 to 9 month transit becomes dramatically safer. If we develop closed-loop life support systems that are genuinely 100% efficient in recycling water, air, and nutrients, something that current technology approaches but has not yet achieved, then the colony becomes dramatically more resource independent from its earliest days. If we develop genetic screening and embryo selection technologies that allow a small founding population to maintain much greater genetic diversity than their raw numbers would naturally permit, a controversial but scientifically plausible approach that some researchers have discussed seriously, then the genetic viability threshold of tens of thousands of individuals might not be the hard constraint it currently appears to be. Any one of these breakthroughs, materializing within the next few decades, could pull the colonization timeline significantly forward. Multiple breakthroughs happening in sequence, as they have consistently done throughout the history of technology, where progress in one domain enables progress in adjacent ones, could compress a 300-year timeline into a 100-year timeline, could make genuine civilizational self-sufficiency a 22nd century reality rather than a 23rd century one. None of that is guaranteed, but none of it is implausible either. And this is where the careful distinction between what the science currently supports and what the science currently forecloses becomes critically important. The science currently supports a timeline of 150 to 350 years to genuine colonization. The science does not foreclose a significantly shorter timeline if specific technological breakthroughs materialize. The range of possible futures is wide, and which future we end up in depends significantly on choices being made right now. Let's talk about what right now actually looks like, because the distance between the abstract and the concrete matters, and the concrete version of right now is both more encouraging and more complicated than most people realize. Right now, in 2026, there are approximately 8 active spacecraft, either orbiting Mars or operating on its surface. Think about that for a moment. 8 separate machines, built by multiple countries, representing decades of engineering effort and billions of dollars of collective investment, are actively working on Mars at this moment, sending data, building our understanding, laying the groundwork. Right now, the largest and most powerful rocket ever built by human hands, SpaceX's Starship, is in active flight testing, iterating toward the capabilities that a Mars mission will require. Its development is happening faster than any previous crewed spacecraft program in history, even accounting for delays and setbacks. Right now, NASA's Perseverance rover is collecting samples in Jezero crater that may contain the most scientifically important material ever assembled. Samples that, when they return to Earth, could answer the question of whether life ever existed on Mars. A question that, if answered yes, changes everything about how we understand our place in the universe. Right now, hundreds of researchers at universities, government laboratories, and private companies around the world are working on the specific technical challenges of Mars habitation, radiation shielding, closed-loop life support, in-situ resource utilization, food production in confined environments, psychological support systems for isolated crews. The research is real, the progress is real, The pace, compared to 20 years ago, is genuinely accelerating. And right now, for the first time in the history of Mars exploration, the serious question is not whether humans will go to Mars. It's when, and what happens next. That shift from if to when is itself one of the most significant developments in the history of space exploration, and it happened within the last decade, within the professional lifetimes of most of the scientists and engineers currently working in the field. There is a phrase that appears repeatedly in the history of transformative human projects. The phrase is the 100th meridian. It refers to a line on the American Great Plains, roughly where the western half of Kansas meets the eastern half of Colorado, the line beyond which rainfall becomes too sparse and unpredictable for traditional dryland farming. Early settlers who crossed that line without understanding what it meant often failed catastrophically. Those who understood it, who adapted their methods, developed new technologies like irrigation and drought-resistant crops, built different kinds of communities suited to a more demanding environment, eventually thrived. Mars is humanity's 100th meridian, the line where everything familiar becomes inadequate and new approaches are required, where the tools and assumptions that worked perfectly well inside the boundary of Earth's biosphere fail, and where survival requires genuine innovation, biological, technological, social, psychological, political. Crossing that line will take longer than the optimists say. It will cost more than the budgets currently allocated. It will require sacrifices that we cannot fully anticipate from here. Some missions will fail, some colonists will die, some political will collapse and need to be rebuilt. Some technologies that we're currently counting on will underperform and need to be replaced by solutions we haven't yet conceived. All of that is true, and none of it means we shouldn't go, because the other side of that line is extraordinary. A second world, a second chance, a second vantage point from which consciousness can look out at the universe and ask its oldest, deepest questions. A living demonstration that the universe is not hostile to the emergence of awareness, that awareness, once it arises, has the will and the capacity to persist and spread, to carry life and light into the darkness between worlds. We are made of the remnants of ancient stars. The iron in your blood was forged in the hearts of massive stars that lived and died billions of years before our sun was born. The calcium in your bones, the carbon in your DNA, the oxygen in every breath you take, all of it was created in stellar furnaces and scattered across the galaxy by supernova explosions before being gathered by gravity into our solar system, into our planet, into the chemistry of life, into you. When we send humans to Mars, when we plant the first seeds of a second civilization on a second world, we are not doing something alien to the universe. We are participating in one of its deepest patterns. Stars forge heavy elements and scatter them. Gravity gathers those elements into new worlds. Life emerges on those worlds and fills every available niche. And eventually, perhaps rarely, perhaps only here, perhaps everywhere, that life develops the curiosity and the capability to reach beyond its home world and carry the story of chemistry and biology and consciousness to new places. We are that life. This is that moment. And the timeline, however long it turns out to be, is already underway. Let's begin at the end. Not the end of the story, because the story we've been telling across this entire video doesn't have an end. Not really. It has a beginning that stretches back 4 billion years to the first self-replicating molecules in Earth's early oceans, and a future that extends further forward than any human mind can honestly contemplate. But let's begin at the end of a specific chapter. The chapter that closes when the first genuinely self-sustaining human community on Mars looks back across the darkness between worlds and sees Earth, not as home, not as the place they came from, not as the authority they answer to, but as a neighbor, When that moment comes, something fundamental will have changed, not just about Mars, and not just about the people living there. Something will have changed about what it means to be human, about where humanity lives, about the shape of our story. And understanding what that change means, really sitting with it, is, I think, the most important thing this video can leave you with. Let's start with the practical dimension, because it grounds everything else. When a self-sustaining Mars colony exists, when a population of tens of thousands or eventually hundreds of thousands of people are genuinely living their lives on another world, building an economy, raising children, developing culture, making art, arguing about politics, falling in love, growing old, Earth will be transformed by that fact in ways that go far beyond the obvious. The most immediate transformation is what you might call the insurance policy. Right now, every human being who has ever lived has lived on Earth. Every human who has ever died, died on Earth. Every civilization that has ever flourished and collapsed, every extinction-level catastrophe that has ever threatened our species, the asteroid impact 66 million years ago that ended the non-avian dinosaurs, the supervolcanic eruptions that nearly collapsed ancient ecosystems, the pandemics and famines and wars that have periodically devastated human populations. All of it happened on one world, one address, one fragile, irreplaceable, pale blue dot. The probability of a civilization-ending catastrophe striking Earth within the next 1,000 years is not zero. Astronomers track near-Earth asteroids with genuine concern, and while no known impactor is currently on a collision course, the history of our solar system is written in impact craters, supervolcanic events, eruptions orders of magnitude larger than anything in recorded human history, like the eruptions that formed the Yellowstone caldera or the Deccan Traps, occur on geological timescales that make them statistically relevant over centuries. Engineered pandemics, runaway climate change, nuclear exchange, the list of civilization-scale risks that humanity faces from its own actions is longer today than it was a century ago, and the trend is not obviously improving. A self-sustaining Mars colony does not make any of those risks go away, but it fundamentally changes what they mean. Because if the worst happens, if Earth is struck by an impactor, or convulsed by a supervolcanic winter, or devastated by a biological or nuclear catastrophe that collapses the complex infrastructure of industrial civilization, there will be people who survive. Not just survive in scattered pockets on Earth, clinging to the margins of a broken biosphere, survive in a functioning, technologically capable civilization on another world with the knowledge and the capacity to eventually help Earth recover, or, if Earth cannot recover on human timescales, to carry the human story forward without it. Stephen Hawking, in one of his final public statements before his death in 2018, said something that has stayed with me. He said that he did not think the human race would survive another 1,000 years without escaping beyond our fragile planet. You can agree or disagree with the specific timeline, but the underlying logic is difficult to dismiss. A species that keeps all of its eggs in one basket, no matter how beautiful and precious that basket is taking a risk that gets more dangerous with every century that passes and every new civilization-scale technology that emerges. Mars is not a backup hard drive for humanity. That framing is too cold, too mechanical for what's actually at stake. Mars is a second home, and the difference between having one home and having two is not quantitative. It's existential, but the transformation goes deeper than insurance. It goes into something harder to quantify, but more fundamentally important: what the existence of a second human civilization does to Earth's own culture, philosophy, and self-understanding. Consider the overview effect again. We talked about it in Part 6, the profound psychological shift that astronauts report when they see Earth from space, the sudden, overwhelming recognition of Earth's fragility, its beauty, its unity, the dissolution of the borders and divisions that seem so absolute from the ground, the visceral understanding that we are all, every one of us, passengers on the same small vessel moving through an incomprehensibly vast darkness. Every astronaut who has experienced the overview effect has had to come back to Earth and try to translate that experience into words for people who have never left. And the translation is always imperfect. Not because astronauts are poor communicators, many of them are extraordinarily articulate, but because the experience is fundamentally perceptual. You can be told that Earth is small and fragile and that its atmosphere is a thin blue line barely visible from orbit. But being told that and seeing it are not the same thing. The emotional, cellular, identity-level impact of actually seeing it cannot be fully transmitted through language. Now imagine an entire civilization that grows up with that view. Not as an extraordinary experience accessible to a handful of specially selected and trained individuals, but as the permanent, unalterable condition of daily life. The people of Mars will see Earth, when it's visible, as a bright blue point of light in a dark sky, not as the world, as a world, one among others, beautiful, precious, but not the totality of human existence. What philosophy emerges from that vantage point? What religion? What art? What political thought? What does justice mean to a civilization that can look across interplanetary space and see with their own eyes the world their ancestors came from, a world they can never easily visit, a world that can never easily help them? What does community mean when the nearest community of human beings is tens of millions of kilometers away? We genuinely do not know. No human civilization has ever faced those questions from that position. We can speculate, drawing on anthropology and philosophy and the history of isolated human communities on Earth, the cultures that developed on remote Pacific islands, in deep Arctic regions, in isolated mountain valleys, but those analogies are all imperfect. The degree of isolation that Mars imposes is qualitatively different from anything in human historical experience. What we can say with confidence is this: the Martian civilization, if it develops and matures, will not simply be Earth culture transplanted to a different address. It will be something new, something shaped by its environment, its isolation, its specific challenges, its specific freedoms, its specific vantage point on the universe. Just as American culture is not simply European culture moved westward, it's something that emerged from the interaction of transplanted people with a new environment, a new scale, new freedoms and new constraints. Martian culture will be something that none of us alive today can fully anticipate, and that new thing, whatever it turns out to be, will flow back to Earth. Through communication, through the exchange of ideas, through the simple fact of knowing that other human beings in an unimaginably different environment are grappling with the same fundamental questions. What is a good life? What do we owe each other? What is worth preserving and what is worth changing? And coming up with different answers. Answers that Earth, looking across the darkness, might find challenging or inspiring or incomprehensible or profoundly clarifying. The greatest contribution of the Mars civilization to Earth may not be any specific technology or resource. It may be the perspective, the living proof that human beings can adapt to radically different circumstances and still be recognizably, deeply, fully human. That our identity is not bound to any particular set of atmospheric conditions or gravitational parameters or childhood landscapes. That what makes us human is something more portable, more durable, more essentially ours than any of those things. Now let's go even larger. Let's zoom out to the scale that I find most genuinely awe-inspiring about this entire story. The universe is approximately 13.8 billion years old. Earth is approximately 4.5 billion years old. Complex, multicellular life on Earth is approximately 600 million years old. Homo sapiens, Our species, anatomically modern humans with the brain structure that makes language and culture and science and art possible, has existed for roughly 300,000 years. Written civilization, the accumulated record of knowledge that makes each generation the inheritor of everything that came before, has existed for roughly 5,000 years. Modern science, the systematic, empirical, self-correcting method of building reliable knowledge about how the universe works, has existed for roughly 400 years. The ability to leave Earth's atmosphere entirely has existed for less than 70 years, against the 13.8 billion-year backdrop of the universe. The interval between the first self-replicating molecules and the first species capable of reaching another world is essentially instantaneous. It happened so fast on cosmic timescales that it's almost hard to believe it wasn't inevitable, that somewhere in the deep logic of chemistry and physics, the emergence of life and eventually of intelligence and eventually of the curiosity and capability to leave home was always going to happen, given time and the right conditions. But was it? That's one of the deepest open questions in all of science, the Fermi paradox. If life tends to emerge wherever conditions allow, and if intelligence tends to follow given enough time, then the universe should be full of civilizations far older than ours, that have had not thousands but millions or billions of years to develop and spread, and yet silence, no signals, no artifacts, no unambiguous evidence of anyone else out there. The most sobering interpretation of that silence, not the only interpretation, but the one that many serious researchers consider most likely, is that the emergence of technological civilization is far rarer than optimistic assumptions suggest. That there is a filter, perhaps many filters, between simple life and the kind of complex, durable, expansionist intelligence that could leave detectable marks on the universe, and that most life, wherever it arises, never makes it past those filters. If that's true, then what we are doing right now, in these early decades of reaching beyond Earth, is something extraordinarily rare. Something the universe may have been waiting billions of years for. Something that, for all we know, is happening for the first time anywhere in the entire observable cosmos. The colonization of Mars, in that context, is not just a human achievement, it is a cosmic event. The moment when a form of organized matter, complex enough to be aware of itself, curious enough to ask questions about the universe that produced it, becomes durable enough to survive the loss of its home world. When life, for perhaps the first time since the universe began, becomes genuinely multiplanetary, that is not a small thing. That is perhaps the largest thing that has happened in this corner of the galaxy in a very long time, and we are the ones doing it. So let me bring it all the way back to the question we started with. How long would it really take to colonize Mars? The honest, evidence-based, scientifically grounded answer is this: the first human foot on Martian soil, somewhere between 10 and 20 years from now, a permanent, continuously occupied outpost, perhaps 20 to 40 years from now, a genuine settlement, a community with children and culture, and the first fragile roots of a new civilization, perhaps 50 to 70 years from now. Early self-sufficiency, the ability to survive without Earth's support for extended periods, perhaps 80 to 120 years from now. Full civilizational independence, a Mars that could carry the human story forward even if Earth fell silent, somewhere between 150 and 350 years from now. Those timelines are not fixed. They are the central tendency of a wide distribution of possible futures. They could compress dramatically if the right technological breakthroughs materialize, if political will sustains itself across decades, if the first missions succeed and build the momentum that early success always generates. They could stretch or fail entirely if the challenges prove harder than expected, if political will collapses, if early missions end in catastrophic failure that poisons public and political appetite for the risk. But here is what I want you to take from this video, beyond any specific number. The question, how long would it really take, has an implicit assumption buried inside it. The assumption that the timeline is something that will happen to us, something determined by forces and decisions outside our individual influence, something we watch from the sidelines. And that assumption is wrong. The timeline for Mars colonization is not a fixed feature of the future. It is a collective choice being made right now, in thousands of small increments, through funding decisions and political priorities and cultural values, and the individual choices of hundreds of thousands of scientists, engineers, policymakers, educators, science communicators, and ordinary people who care about where our species is headed. The scientists designing radiation shielding in university labs right now are shaping the timeline. The aerospace engineers iterating on closed-loop life support systems are shaping it. The politicians who choose to fund planetary science rather than cut it are shaping it. The teachers who inspire a 12-year-old to fall in love with physics are shaping it, because that 12-year-old might be the person who solves one of the critical problems standing between us and Mars. And the people who watch videos like this one, who stay curious, who share what they learn, who keep the conversation alive in their families and communities and social networks, who refuse to let the scale of the challenge become an excuse for apathy. Those people are shaping it too. More than they know, we are, right now, living through the opening pages of the most extraordinary chapter in human history. Not the most comfortable chapter. The chapter ahead involves sacrifice and failure and grief and the kind of slow, grinding, patient effort that doesn't make for dramatic headlines. But the most extraordinary, the chapter where the species that looked up at the stars for hundreds of thousands of years and wondered finally reaches one of them, not metaphorically, not in simulation. Actually, physically, irreversibly reaches out and touches another world, and begins with all the awkwardness and courage and creativity and fallibility that have characterized every great human venture to make it home. The universe is 13.8 billion years old. It has been here vast and silent and mostly dark for an incomprehensible span of time. Stars have been born and have died. Galaxies have collided and merged. Black holes have swallowed entire stellar populations and emitted their energy as jets of plasma that crossed millions of light years before dissipating in the intergalactic void. And somewhere in that vast dark tapestry, on one small rocky world orbiting one ordinary star, something woke up, looked around, began to ask questions, built tools, told stories, looked up at the night sky and felt a pull it couldn't name but couldn't ignore, and is now, haltingly and ambitiously, and with full knowledge of the cost and the risk and the difficulty, reaching out toward Mars, toward what comes after Mars, toward a future that none of us will live to see in full, but that all of us are building with every day we choose to remain curious, to remain engaged, to remain committed to the idea that the universe is worth exploring and that we are the ones who get to do it. That is the answer to how long it would really take to colonize Mars. It will take as long as we decide it takes, and it has already begun. If this blew your mind, the video on the screen will break it completely. We explore the harsh reality of actually living on Mars. It will completely change how you think about everything we just talked about. See you there.